All right, people. So let's get started then. Let's get started with the first topic, that is your Planck's quantum theory, right? So first of all, what this Planck's quantum theory exactly is all about, what kind of questions are asked from this, right? Let's get to know about the Planck's quantum theory. My dear students, the first statement, I want you guys to write all the things with me because every single thing is going to be very important. Equilibrium will be also done, no need to worry, right? The next chapter which I'm doing, that is going to be from the organic part. I think I'll be doing the next chapter, that is amines, complete amines in one shot, okay? That is going to be the next chapter. Class 12th organic chemistry chapter is there, amines, right? From which you can expect 2 questions. That's going to be our next chapter here. I'll be teaching that. Perfect. I want you guys to take a note of every single thing. Whatever I'll be writing on the screen, please and please, every single thing is going to be important, right? Perfect. And I'll be giving you only that much amount of theory which is required to solve the questions. That much amount of theory which is required to solve the questions of your NEET examination. Okay? Perfect. So, Planck's quantum theory. My dear students, according to this particular theory, energy is transmitted. According to this particular theory, energy is transmitted. Energy is transmitted in the form of small packets. In the form of small packets. In the form of small packets. And my dear students, you should be calling those small packets. You should be calling those small packets as, one small packet is called as quantum, right? What does it mean exactly? My dear students, for example, over here, you have got a source of energy. Let's say it is a source of energy. It is the source of energy. I'm assuming that this particular source of energy, it is emitting energy. It is emitting energy, right? I'm assuming the source of energy which I have over here. My dear students, let's assume that this particular source of energy is emitting energy in the form of radiations. It is emitting energy in the form of radiations. What Planck's quantum theory is all about? Planck's quantum theory says that these radiations, right? They consist of small packets. They consist of small packets. And these small packets, they have got a particular, a fixed, a discrete value of energy with them. These small packets, they have got certain amount of energy, right? And these small packets, of which your radiations consist of, these small packets are what you call as quantum. One packet is called as quantum and more than one packet is called as quanta. Perfect, right? And my dear students, whenever particularly you talk about light radiation, in case of light radiation, this quantum is what you call as photon. In case of light radiation, this quantum is what you call as photon. So basically, from now onwards, remember that as per Planck's quantum theory, energy is transmitted in the form of small packets. Those small packets, they have got some amount of energy with them. Those small packets in general are called as quanta. If I talk about light radiation in particular, in case of light radiation, those small packets are what you call as photons. Is this clear to everyone? Is this clear to everyone? Imagine this is the light radiation. Imagine this is your light radiation, my dear students. So this light radiation, it consists of the small packets, and these small packets over here are what you call as photons. These small packets are what you call as photons, right? These small packets are what you call as photons, particularly in case of light energy. Number one. Number two. My dear students, the energy which will be associated with one photon. Energy associated with one photon. Energy associated with one photon. One photon carries the energy which will be equal to h nu. H nu. Or it can be written as hc divided by lambda. It can be written as hc divided by lambda. This is the energy carried by one photon. Now the point is, what is nu and what is lambda? My dear students, nu is what you call as frequency of the light radiation, right? And lambda is what you call as wavelength of the light radiation, right? Wavelength of the radiation. Perfect. Energy associated with one photon, that's equal to h nu, or you can write it as hc divided by lambda, right? What is c? C is the speed of light. You know it already. 3 into 10 raised power 8 meter per second, right? Perfect. I hope this is clear to everyone. Now, my dear students, if this is the energy associated with one photon, if I ask you what will be the energy associated with two photons, it will be 2 times this. Energy associated with 3 photons, 3 times this. If I ask you what is going to be the energy associated with n photons, what will be the energy associated with n photons? You will directly say it's going to be n times h nu, or you can say n times hc divided by lambda. This is the energy associated with n number of photons. This is the energy associated with n number of photons. My dear students, what this h over here is all about? What this h is? H is a Planck's constant. You should be knowing it. 6.6 into 10 raised power minus 34 joules second. This is the value of it. Know it as well. Perfect. Now, dear students, one more important thing. What is that? Do remember the value of h multiplied by c. The value of h multiplied by c. H is a constant, c is a constant. If you multiply them, h multiplied by c, it will be written as 12400 electron volt angstrom. H multiplied by c, its value will be taken as 12400 electron volt angstrom. When lambda is taken in angstroms. When lambda is taken in angstroms. And do remember the value of h multiplied by c, it will be taken as 1240 electron volt nanometer when lambda is taken in nanometers. When lambda is taken in nanometers. This is one more important thing which will reduce your calculation. This is one more important thing which will reduce your calculation, my dear students. Right? Now, one more thing which I would want to share with you here. If you ask me, sir, what are the units of energy? What are the units of energy? My dear students, as you all must be familiar with the fact, SI unit of energy, SI unit is going to be joule. SI unit is going to be joule, right? This is the SI unit of energy. And over here, I'll be using one more unit of energy. That is going to be electron volt. This will be also used frequently. Joule will be used. Electron volt will be used. And do remember, 1 electron volt is nothing. It is 1.6 into 10 raised power minus 19 joules, right? I'll be using this particular term over here as well. Perfect. SI unit of energy is joules. There is one more unit of energy which is used. That is electron volt. Perfect. And do remember, 1 electron volt is nothing but 1.6 into 10 raised power minus 19 joules. I hope this is clear to everyone. So as per Planck's quantum theory is concerned, energy is transmitted in the form of small packets. You call those small packets as quantum, right? Particularly in case of light radiation, those small packets are called as photons. This is the energy associated with one photon. This is the energy associated with n photons, right? H multiplied by C value will be taken as 12400 electron volt angstroms when lambda will be in angstroms. H multiplied by C value will be taken as 1240 electron volt nanometer when lambda will be taken in nanometers, right? And my dear students, the units of energy, you know it. SI unit is joule. There'll be one more unit which I shall be frequently using, that is electron volt. And do remember, 1 electron volt is nothing. It is 1.6 into 10 raised power minus 19 joules, right? Is it clear to everyone? Say yes or no in the chats quickly. Quickly, people. If this is clear, then I'll show you one simple question which will make this concept clear. Quickly, let me know in the chats. Every one of you. And you'll be getting the PDF of this particular session in the Telegram. I hope all of you are in my Telegram, right? I hope all of you are already in my Telegram. Perfect. Right? So this is something which I told you till now. According to this theory, Okay, this is something which I told you till now. According to the theory, energy is transmitted. In case of light energy, these packets are called as photons. Photon travels with the speed of light in vacuum, right? Energy possessed by one photon, energy possessed by n photons. Now, SI unit of energy is joule. 1 electron volt is this much with the value of Hc. This is something which I believe is clear to everyone. Okay. Now, people, look at this particular question. The first question which is on your screen. Calculate the energy of 100 photons if the wavelength of light is 2000 angstrom. Isn't it simple? Isn't it simple? Calculate the energy possessed by 100 photons. You know, energy carried by n photons. Energy carried by n photons is equal to n times hc divided by lambda. So therefore, I can say energy carried by 100 photons. Energy carried by 100 photons will be equal to 100 multiplied by the value of h multiplied by c. Since lambda is in angstroms, so h multiplied by c value I'll be taking as 12400 electron volt angstroms divided by lambda is already in angstroms, which is 2000 angstroms. So angstrom cancels out. So you'll be getting the value in electron volts here. You'll be getting the value in electron volts here. Is it clear? A very simple and basic question. How much the value comes out to be? Well, people are saying the value is coming out to be 620 electron volts. So this is the energy which is carried by 100 photons who have got the wavelength of 2000 angstroms. Now, if you ask me, sir, calculate the same energy in joules. You know, 1 electron volt is equal to 1.6 into 10 raised power minus 19. The value is going to be in joules. They can ask you either the value of energy in electron volts or they can ask it in joules. I believe this is clear. I believe this is clear. Look at the second question, my dear students. Look at the second question. I hope you can quickly solve it. A light source of wavelength. A light source of wavelength. You have got a source of light which is emitting light, right? That light has got the wavelength of 2000 angstroms, right? Energy possessed by the radiation is 0.5 joules. The number of photons emitted from the source. The number of photons emitted from the source, right? So my dear students, how you are going to do it? See, energy carried by the light radiation is equal to, I'll write n times hc divided by lambda. N times hc divided by lambda, right? What do we have to calculate? Number of photons which are emitted from the source. We have to get the value of n. So over here, E value is given as 0.5 joules is equal. On left hand side, I'm using joules. So on right hand side, I'll have to use joules as well. If left hand side is in joules, then right hand side should be in joules as well. Right hand side should be in joules as well. Correct? Now guys, this n can be as such. N can be as such. H multiplied by C can be written as 12400 electron volt angstroms divided by lambda value is given to us as 2000 angstroms. So if angstrom gets cancelled out, the right hand side will be in electron volts. But do I need the right hand side in electron volts? No. I need the right hand side in joules as well. And this electron volt. 1 electron volt is how much? 1 electron volt is how much? 1.6 into 10 raised power minus 19. Therefore, left hand side as well as right hand side, both are in joules. Now you can do the multiplication, cross multiplication, whatever you want to do, and you can get the value of n over here. And that n is something which we were supposed to calculate. Is that clear to everyone? Is that clear to everyone? Or my dear students, you can do the calculation like this as well. You can do the calculation like this as well. E is equal to 0.5 joules. Left hand side is in joules. So right hand side has to be in joules as well. If right hand side has to be in joules, that means right hand side has to be as per SI system. So everything over here has to be in SI system, right? So n as such, value of H as per SI system, 6.6 into 10 raised power minus 34. C value as per SI system, 3 into 10 raised power 8 meter per second. Lambda value as per SI system, 2000 into 10 raised power minus 10 meters, right? From here, you can get the n value as well. Perfect. The choice is all yours, whatever approach you want to do. Perfect. I hope this is clear. Now, there is something called as power. There is something called as power, right? Which is defined as P. How do you exactly define the power of the source? My dear students, power is defined as energy emitted by the source. Energy emitted by the source divided by what? Divided by time. Energy emitted by the source divided by time. So power is nothing, E divided by T. Perfect. Power is nothing but E divided by T. Let's say you have got a source of energy. It is emitting radiations. Let's say it is emitting the light radiation, right? Let's say it is emitting the light radiation. Perfect. Let's say this light radiation, it consists of n photons. Let's say this light radiation consists of n photons. So if I ask you, since this source of light, this source of energy, it is emitting light radiation. That light radiation carries n photons. If I ask you, how much energy is emitted by this? How much energy is emitted by this source? How much is that going to be? That is going to be energy emitted by the source is going to be n times h nu divided by time taken. This is the general result by means of which you can calculate power. You can calculate power. Or my dear students, you can write it like this. Power of the source is equal to n times, right? H I'm writing as such. Nu is equal to C divided by lambda. Nu is equal to C divided by lambda. So this can be one more result which you can use to calculate the power of the source. This can be one more result which can be used to calculate the power of source. I believe this is clear to everyone. Okay. What is N divided by T here? What is N divided by T here? This is something which you call as rate of emission of photons. N by T combinedly is called as the rate of emission of photons. Okay. Rate of emission of photons. This N divided by T I'm talking about. This N by T is something which you call as rate of emission of photons. And my dear students, you know what is the SI unit of power? You know it is nothing but watt. I hope this is again clear to everyone. Right? Okay. So power is nothing. It is energy emitted divided by time taken. Right? Energy is NHC divided by lambda divided by T. N divided by T. You call it as the rate of emission of photons, or you can call it as number of photons emitted per unit time. Number of photons emitted per unit time. N by T. Okay? Alright. Look at this particular question. People. How many photons are emitted per second? Right? How many photons are emitted per second? So basically you are supposed to calculate N by T. You are supposed to calculate the rate of emission of photons. How exactly you are going to do that? I told you a result a few minutes back. Power is equal to N times Hc divided by lambda divided by T. N by T value you have to calculate. N divided by T value you have to calculate, which is going to be power multiplied by lambda divided by Hc. Perfect. Now, you have got how many photons are emitted per second by a 5 milliwatt laser. So power of the laser is 5 into 10 raised power minus 3 watts. And this laser is operating at 620 nanometer wavelength. 620 nanometers, right? 620 nanometers. Yes, 620 nanometers. Now you just have to put the values over here. You'll be getting the N by T value. What is N by T? N by T means the rate of emission of photons. N by T means number of photons emitted per second. Isn't it simple, people? Let me know once in the chats quickly. Isn't it simple? Can't hear, sir. Guys, am I audible to you? Just a second, let me check. Yes, I'm perfectly audible. Yes, I'm perfectly audible. Right? I think I'm perfectly audible. Yes? Perfect, guys? Right? So, my dear students, this can be written as 620 multiplied by 1 nanometer is 10 raised power minus 9 meters. So, this as per SI system, this as per SI system. So, power is 5 into 10 raised power minus 3 watts, right? Lambda 620 multiplied by 10 raised power minus 9 meters, right? H value 6.6 into 10 raised power minus 34, and C value is 3 into 10 raised power 8 meter per second. I used all these values as per SI system. And eventually I'll be getting the rate of emission of photons. Eventually I'll be getting the number of photons emitted per second. That is something which I was supposed to calculate in this particular equation. If this is clear, let me know once in the chats. If this is clear, let me know once in the chats. If this is clear, let me know once in the chats. With some fire emojis. Quick. Quick, guys. If this is clear, let me know once in the chats. With some fire emojis. Everyone. Everyone. Yes? Perfect. Now, there is something called as photodissociation. What is photodissociation all about? How do you define the term photodissociation? Photodissociation is defined as breaking of a chemical bond using light energy. Breaking of a chemical bond using light energy. For example, let's say there is a bond between chlorine and chlorine. Let's say there is a bond between chlorine and chlorine. What is a bond? It is a force of attraction which is holding these atoms together. It is a force of attraction which is holding these atoms together. My dear students, for example, I need to break this bond. I need to break this bond. In order to break this force of attraction, what do I have to do? I have to supply energy. In order to break this bond, in order to break this force of attraction, I need to supply energy. Imagine I'm supplying energy in the form of photons. Imagine I'm supplying energy in the form of light radiations. And after supplying photons, after supplying light radiations, after supplying energy in the form of photons, imagine the bond got broken down. Imagine the bond got broken down. That breaking of a bond with the help of light energy is something which you call as photodissociation. Right? I believe this is clear. I believe this is clear. That breaking of the bond with the help of light radiation is something which you call as photodissociation. Now, my dear students, here you have to understand few important things. Here you have to understand few important things. For example, there's a bond between, let's say, A and A. There's a bond between A and A. There's a force of attraction between A and A. Now, my dear students, if you need to break this bond, what do you need? You're supplying energy. Imagine you're supplying energy in the form of photons, right? Imagine you're supplying energy in the form of photons. Perfect. And energy associated with the photon, you know it? It is equal to h nu. It is equal to h nu. Imagine I would require n photons. Imagine I would require n photons to break this bond. Imagine I would require n photons to break this bond. So, how much energy in total is required to break this bond then? It is equal to n times h nu. This is the energy which is required to break this bond. Okay. Now, my dear students, for example, I'm writing a term here. Bond energy of A2 is equal to x kilojoules per mole. I'm writing a term here. Bond energy of A2 is equal to x kilojoules per mole. What does that mean? That means in order to break 1 mole of bonds, how much energy is required? X kilojoules of energy is required. That's the meaning of it, right? In order to break 1 mole of bonds, X kilojoules of energy is required. Now, 1 mole bonds means how many bonds? Na bonds. So, in order to break Na bonds, how much energy is required? X kilojoules, right? In order to break Na bonds, X kilojoules of energy is required. So, in order to break 1 bond, how much energy is required? X divided by Na kilojoules. So, this much amount of energy is required to break. This much amount of energy is required to break 1 bond. This much amount of energy is required to break 1 bond. Am I breaking 1 bond? Yes. Right? I'm breaking 1 bond with the help of n number of photons. Energy carried by n photons is n times h nu. It is equal to n times h nu. My dear students, this amount of energy is used to break 1 bond, right? And this much amount of energy I am providing with the help of photons. This much amount of energy I am supplying in the form of photons. In the form of how many photons? N photons. So I can relate it with n times h nu. I can relate it with the help of n times h nu, right? Or I can write it like this. X divided by Na. X divided by Na. This is in kilojoules. Keep it in kilojoules. You can later on convert it into joules. Is equal to n times, this can be h, nu can be written as C divided by lambda. Nu can be written as C divided by lambda. Perfect. Nu can be written as C divided by lambda. So from this particular expression, what can we calculate? We can calculate a lot of things. How many photons are required to break a bond, given that bond energy was X kilojoules, right? Given that bond energy was X kilojoules. Perfect. Can you make this sort of expression always? Can you make this sort of an expression? I can generalize it. You need not to do all these things again and again. So let's generalize it. What was this X? X was the bond energy. Divided by Avogadro's number is equal to number of photons required to break the bond multiplied by Hc divided by lambda. Lambda is the wavelength of the photons which are incident on this bond. This is the general result which I would want you guys to remember. Okay. One thing you need to be careful with. If left hand side you are using kilojoules, right hand side also you have to use in kilojoules as well. That means the units on both the side, left hand side and right hand side, should be equal. Should be the same. Yeah? Should be the same. I believe all these things are clear. If these things are clear, let's try to solve one question. It becomes automatically clear with the help of the question. Calculate the wavelength of the photon. Calculate the wavelength of the photon of light required to break Cl-Cl bond. If the bond energy of Cl-Cl bond is 1.2 kilojoules per mole, I have to calculate wavelength of the photon. That means one photon is enough to break one bond. Right? That means one photon is enough to break one bond. Perfect. That means you have got a Cl-Cl bond. Its bond energy is given to us. How much is the bond energy? Bond energy is given to us as 1.2 kilojoules per mole. Okay. Perfect. I need to break this bond. In order to break this bond, one photon is required, whose energy will be equal to h nu or hc divided by lambda. Perfect. Whose energy is equal to h nu, hc divided by lambda. So first of all, what kind of the result I'm going to use? I'll show you the general approach first. My dear students, in order to break one mole bond, how much energy is required? 1.2 kilojoules of energy is required. Let's convert this in joules here only. 1.2 into 10 raised power 3 joules of energy is required to break one mole of bond. That means in order to break Na bonds, how much energy is required? 1.2 into 10 raised power 3 joules. So in order to break one bond, how much energy is required? 1.2 into 10 raised power 3 divided by Na joules. So this much amount of energy is required to break one bond. Imagine this much amount of energy I'm supplying in the form of photon, right? So I can say 1.2 multiplied by 10 raised power 3 divided by Na has to be equal to Hc divided by lambda. Perfect. Hc divided by lambda, where lambda is the wavelength of the photon which is incident on the bond. Perfect. Now it is just the matter of calculation, nothing else. So it can be written like this. My dear students. 1.2 into 10 raised power 3 divided by Na is equal to H. You already know 6.6 into 10 raised power minus 34. C is your 3 into 10 raised power 8 meter per second divided by lambda. Lambda will be here in meters. Why lambda will be in meters? See, your left hand side is in joules as per SI system. Therefore, right hand side has to be in joules as well as per SI system. For right hand side to be in joules, this has to be as per SI system. This has to be taken as per SI system. Therefore, lambda will come as per SI system. So from this particular equation, you can calculate lambda in meters, which will give you the wavelength of the photon which was incident on the bond. If it is clear, let me know once in the chats. Quickly, people. If it is clear, let me know in the chats quickly. Quickly. Yes or no? Yes or no? Yes or no? Yes or no? Quick. Look at this particular question. Read the question carefully. Calculate the number of photons required to dissociate 1 mole of Cl2. So here you are not dissociating one bond. Here you are dissociating 1 mole. 1 mole bonds. Right? See, it's very simple. If I talk about one Cl2 molecule, one Cl2 molecule means one Cl2 molecule contains 1 bond. One Cl2 molecule contains 1 bond. Now, if I write something like this, 1 mole Cl2. 1 mole Cl2 contains 1 mole bonds. It's simple. 1 molecule of Cl2 contains 1 bond. Therefore, 1 mole Cl2 contains 1 mole of bonds. And here in this question, you are not supposed to break 1 bond. You are supposed to break 1 mole of bond. You are supposed to break 1 mole of bond. Perfect. Now see, look at the question carefully. Calculate the number of photons required to dissociate 1 mole of Cl2 into Cl atoms if the bond energy of Cl is given as how much? Bond energy of Cl is given as 1.2 kilojoules per mole. Now what does it mean? What does it mean? What does it mean? It means that in order to break 1 mole bonds, how much energy is required? 1.2 kilojoules. In order to break 1 mole of bonds, this much amount of energy is required. Imagine this much amount of energy in order to break 1 mole of bonds. I'm providing in the form of n photons. So it has to be n times hc divided by lambda. N times hc divided by lambda. Perfect. Perfect. So it is going to be 1.2 into 10 raised power 3. Left hand side I'm using in joules. Number of photons I need to calculate. H value is nothing but 6.6 into 10 raised power minus 34 joule second. T is nothing but 3 into 10 raised power 8 meter per second. Lambda here will come in meters, right? And how much is lambda given? How much is lambda given? Lambda n given as 2000 angstroms. So it will be into 10 raised power minus 10 meters. Why? Why I did this conversion? Because left hand side was in joules. Left hand side was in SI system. Right hand side has to be in SI system as well. That's why I use the value of H as per SI system. I use the value of C as per SI system. I use the value of lambda as per SI system. And my dear students, here in this particular question, you can get the value of N. What is N? N means the number of photons which are required to break 1 mole bond. Am I clear with this? Am I clear with this? Quickly, let me know in the chats. Quickly, my dear students, let me know in the chats if I'm clear with this. Am I clear with this? Yes? Is it all clear? Is it all clear? Quickly, quickly in the chats. Everyone. Everyone. Everyone means everyone. Quick, 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 quick. Yeah? Perfect. Now, I believe photoelectric effect you would have discussed in your physics, right? Yeah? By the way, there will be extra problem practice of this chapter, which I'll take day after tomorrow. Okay, in the daytime. There will be some 100 questions extra which I'll be solving for this particular chapter. No need to worry about the question practice. I'll be taking extra session for it. Okay? Photoelectric effect. My dear students, there are few things which you need to remember about photoelectric effect. Okay? Understand what they are. Understand what they are. So first of all, photoelectric effect. What kind of nature of light it shows? See, you know, light shows dual nature. Light shows dual nature. Wave nature as well as particle nature. This photoelectric effect which we are going to discuss, it strongly supports the particle nature of light. It strongly supports the particle nature of light. Number one. Number two, what happens in photoelectric effect? My dear students, imagine this is your metal surface. Imagine this is your metal surface. On the metal surface, what do we have? We have got the positively charged kernels and there are electrons. On the metal surface, we'll have positively charged ions, positively charged kernels and the electrons. Now, if I ask you whether this electron, whether it is free or bounded, whether this electron is free or bounded, I'll say this electron, it will be attracted by all these positively charged ions, right? This electron, if I select one electron here, this is the electron which I'm selecting. This electron will be held here. there'll be attraction between electron and these positively charged ions, positively charged kernels, right? They're not able to see. Let me show it over here. What I'm trying to say is, let's say this is the metal surface. Let's say this is the metal surface. Imagine this is the metal surface of cesium. Imagine this is the metal surface of cesium. So on this surface, what do we have? We have got CS positive ions. There will be CS positive ions. There'll be CS positive ions. And with these CS positive ions, there'll be electrons as well. There'll be electrons as well. There'll be C of electrons. C of electrons. Now, if I ask you whether this electron is free or bounded, this electron is bounded. This electron is being attracted by this CS positive. This electron is attracted by this CS positive, which makes this electron bounded. It's not free, right? So my dear students, tell me one thing. If I want to take this electron out, if I want to take this electron out from the metal surface, since there are attractions between the electron and these kernels, if I want to take this electron out, can I say I have to break this force of attraction? Absolutely, I have to break this force of attraction. In order to break the force of attraction, what do I need to do? In order to break the force of attraction, I need to supply energy. And imagine I'm supplying energy in the form of light, in the form of photon, right? What is going to happen? What is going to happen? When photons will be incident on this metal surface, right? What will happen? Some of the electrons will leave the metal surface. Electrons will be ejected here. Electrons will be ejected here, right? Electrons will be ejected here. Look at the statement. When light is incident on a certain metal, electrons are emitted. Electrons are emitted. And those electrons which are emitted, those are what you call as photoelectrons. The electrons which are emitted, those are what you call as photoelectrons, right? The current which flows due to the motion of photoelectrons. The current which flows due to the motion of photoelectrons. See, no doubt, energy is incident on the metal surface. Electrons are being emitted. When electrons are emitted, there will be directional movement of electrons. There will be movement of electrons in particular direction due to which current gets generated. And that current which gets generated is something which you call as photocurrent. That is what you call as photocurrent. And this phenomenon overall is something which you call as photoelectric effect. So what happens in photoelectric effect? Light, photons, they fall on the metal surface. When they fall on the metal surface, electrons are emitted from the metal surface. This phenomenon of the emission of electrons when light of particular energy falls on the metal surface, this phenomenon is what you call as the photoelectric effect. This phenomenon is what you call as the photoelectric effect, right? My dear students, there are few things which you need to notice over here. What is that? Can any photon take this electron out? Can any photon take the electron out? If I ask you a question, can any photon take this electron out? Not all the photons can take the electrons out. Not all the photons can take the electron out. Right? What I'm trying to say is, try to understand. Have a look. There is a minimum amount of energy which is required. There is a minimum amount of energy which is required to take the electron out. And that minimum amount of energy which is required to take the electron out, that's called as threshold energy or work function. That's called as threshold energy or the work function. So what is threshold energy? It is the minimum amount of energy which is required to take the electron out. That minimum amount of energy which is required to take the electron out, that's something which you call either as work function or threshold energy. Right? And this work function, it is the characteristic of metal. That means every metal has got different work function. Every metal has got different work function. Every metal has got the different work function. Perfect. I'm not going into the details. I'm just telling you that amount of theory which will be required to solve the questions. Okay? So that minimum amount of energy which is required to knock out the electron from the metal surface, that minimum amount of energy is something which you call as work function. And my dear students, this work function, it is represented by phi naught. As per the formula, it's equal to h nu naught, or you can say hc divided by lambda naught. hc divided by lambda naught. So what is this phi naught over here? This is something which you call as work function. This is the minimum amount of energy which is required to take the electron out. What is this nu naught here? This is something which you call as threshold frequency. This is something which you call as threshold frequency. How do you define the threshold frequency? How do you define the threshold frequency? How do you define the threshold frequency? It is the minimum frequency. It is the minimum frequency. It is the minimum frequency which this photon carries. It is the minimum frequency which this photon carries to knock out the electron. To just knock out the electron. That minimum frequency which the photon carries to just knock out the electron, that is something which you call as threshold frequency. That is something which you call as threshold frequency. The minimum frequency which the photon carries, right, to just knock out the electron. Minimum frequency required. If this is minimum, that means this has to be maximum. So what is this lambda naught? This is called as threshold wavelength. This is called as threshold wavelength. So how do I define the threshold wavelength? This will be the maximum wavelength required to take the electron out. Khatam. Right? So there are three terms which I gave you. There are three terms which I gave you. One is work function. One is threshold frequency. One is threshold wavelength. Work function is the minimum energy that is required to knock out the electron. Minimum frequency required. Maximum wavelength required. These are the three terms which you need to remember. That's it. Yes? Right? Right. Am I clear? Am I clear? Quickly in the chats. Am I clear? Am I clear, people? Quickly in the chats. Yes? Now, people, if I ask you, what should be the conditions? What should be the conditions which needs to be followed for the photoelectric effect to happen? Conditions to be followed. Conditions to be followed. For what? For photoelectric effect. Conditions to be followed for photoelectric effect. So first of all, energy of the incident photon. Energy of the incident photon has to be greater than that of, has to be greater or equal to that of threshold energy. Energy of the incident photon should be greater or equal to than that of work function. Right? Or this is the energy of the incident photon, which is basically h nu. So h nu has to be greater or equal to h nu naught. This was the first condition. So here I can generalize one more statement. Nu has to be greater or equal to nu naught. The frequency of the incident photon. The frequency of the incident photon should be greater or equal to threshold frequency. The frequency of the incident photon should be greater or equal to the threshold frequency. Right? Or I can make one more. What is nu? Frequency. C divided by lambda. Right? Nu naught. C divided by lambda naught. C cancel if I take the reciprocal. So lambda should be less or equal to lambda naught. There's one more condition. What is meant by this? This is wavelength of the incident photon. Wavelength of the incident photon should be less or equal to threshold wavelength. Either you can remember it like this, or you can remember it like this, or you can remember it like this. Am I clear with this? Conditions for the photoelectric effect to happen. Energy of the incident photon should be greater or equal to work function. Right? Frequency of the incident photon should be greater or equal to the threshold frequency. Wavelength of the incident photon should be less or equal to threshold wavelength. Right? Am I clear? Am I clear? Am I clear? Am I clear? Am I clear, my dear students? Am I clear? My dear students, just look carefully. Look carefully. This is the metal surface from which you have to take the electron out. Okay? Imagine this is a photon which is incident on the surface. Imagine the photon carries 100 joules of energy. Imagine the photon carries 100 joules of energy. This is the incident energy. Imagine that minimum 30 joules or minimum 60 joules is required to take this electron out. I'm supplying 100 joules. I'm supplying 100 joules. But how much minimum energy is required? 60 joules. So when the electron comes out, it will be having some kinetic energy as well. And if I ask you how much kinetic energy it will have, 100 joules was incident, out of which 60 have been utilized to take the electron out. The remaining 40 joules will be imparted to the electron in the form of its kinetic energy. So can I say whatever energy is incident on the surface, that is broken in two parts? One is your work function and another is your maximum kinetic energy. This is something which you call as photoelectric equation. This is something which you call as your photoelectric equation, right? Now you can make different types of results over here. And what are the results? Incident energy is h nu. This is h nu naught plus kinetic energy maximum. You can remember it like this. You can remember it like this, right? Number one. Number two, you can write h nu is c divided by lambda. H c divided by lambda naught plus kinetic energy maximum of the photoelectron, right? You can remember it either ways. You can remember it either ways. I believe this is clear to everyone. I believe this is clear to everyone. Right? I believe this is clear to everyone. Or my dear students, you can write this particular result in the form of stopping potential as well. Incident energy is equal to phi naught plus E times V naught, where V naught is something which you call as stopping potential. V naught is something which you call as stopping potential. Stopping potential. If I ask you, how do you define the stopping potential? If I ask you, how do you define the stopping potential? How do you define the stopping potential? The minimum reverse voltage which has to be applied to stop the most energetic photoelectron. I believe you would have studied that in physics as well, right? The minimum reverse voltage which has to be applied to stop the most energetic photoelectron. Okay, I want you guys to remember these four results. Well, you can remember this just one, and all the other you can make on your own. Am I clear with this? Am I clear with this? Say yes or no in the chats quick. Am I clear with this? Say it quick, say it quick. Say it quick. This is something which I told you. The incident energy on the metal surface is used in two parts. First, to eject the electron. Second, to provide the kinetic energy to the ejected electron. Right? From where you got the equation. Now people, if I ask you to plot these graphs, can you plot these graphs? Can you plot these graphs? The first graph is between kinetic energy and frequency of the incident light. Kinetic energy and frequency of the incident light. You know your result. That is energy of the incident light is equal to phi naught plus kinetic energy maximum. Right? This was your h nu is equal to, this was your h nu naught plus kinetic energy maximum. Correct? I can write it like this as well. Kinetic energy maximum is equal to h nu minus h nu naught. Now you are plotting kinetic energy along y-axis. You are plotting frequency along x-axis. Right? Kinetic energy you are plotting along y-axis. Frequency you are plotting along x-axis. So this has to be your m and this overall has to be your c. So y is equal to mx minus c. Y is equal to mx minus c. Tell me what is the nature of the graph for y is equal to mx minus c. Quick people. Tell me the nature of the graph. Y is equal to mx minus c. Y is equal to mx minus c. It's not plus c, it's minus c. So the graph will be starting below the origin. Right? It will be like this. If I ask you what about the slope of this curve? Slope of this curve means m, and m is nothing but h. If I ask you what about this intercept? Intercept is c, and c over here is h nu naught. C is h nu naught. I believe I'm clear. Now, this is stopping potential versus frequency. Stopping potential versus frequency. I gave you a result. Incident energy is equal to work function plus E V naught, where V naught is the stopping potential, right? This is your h nu. This is your h nu naught plus EV naught, or I can say EV naught is equal to H nu minus H nu naught, or I can say V naught is equal to H divided by E nu minus H divided by E nu naught. Correct? So if you look at it very carefully, this nu naught you are plotting along y-axis. Perfect. This nu you are plotting along x-axis. This x, this is y. So y is equal to mx minus c. Y is equal to mx minus c. So the graph will again start down the origin, right? Like this. Perfect. If I ask you what about the slope of this graph? What about the slope of this graph? Slope means m. M value is h upon e. What about the intercept? Intercept is h upon e. Intercept is h upon e nu naught. I hope I'm clear with this. Look at this one. Kinetic energy versus intensity. Well, in order to make this curve, I need to tell you few more things. Then only I can make this particular curve, right? And what are those things which you need to know? Conclusions. Conclusions, observations. Conclusions, observations of what? Of photoelectric effect. Remember them directly. Remember them directly. My dear students, tell me one thing. If you increase the frequency of the incident light, if you increase the frequency of the incident light, that means you are increasing the energy of incident light. You are increasing the frequency of the photon, of the incident photon. That means energy of the incident photon is increasing. Due to which some part of energy will be used to take the electron out, while the remaining part will be used to give the kinetic energy to that ejected electron, right? Can I say more the frequency of the incident photon, more the energy of the incident photon, which eventually tells you more is going to be the maximum kinetic energy of the incident of the photoelectron, right? Of the photoelectron, more will be the kinetic energy. If more is the kinetic energy, of that photoelectron which is emitted, can I say more reverse potential has to be given to stop that? Can I say more will be the stopping potential? Can I say more will be the stopping potential? This is one very, very, very important statement. This is one very, very, very important statement. Right? Right, people? So more the frequency of the incident light, more the frequency of the incident photon, more is the energy of the photon, right? More energy of the photon means more will be the kinetic energy imparted to the photoelectron. More reverse potential has to be applied to stop that photoelectron to reach the anode. Correct? I hope this is clear. Number one. Number two. This photoelectric effect is also called as one photon. It is also called as one photon, one electron emission. One photon, one electron emission. Why is that? It means that one photon can always knock out one electron. One photon can always knock out one electron. One photon cannot knock out two electrons. One photon can knock out just one electron. One photon can never knock out two electrons. Why am I telling you this? Because there might be some misunderstandings here. For example, this one electron. Let's say the work function of this metal is 50 joules. That means minimum 50 joules energy is required to take the electron out. Okay. For example, this is one photon which is incident. This one photon carries 100 joules of energy. This one photon, it carries 100 joules of energy, right? And minimum energy required to take the electron out is 50. Does that mean this one photon will take two electrons out? Because this requires 50, this requires 50, 50 plus 50 is 100. Does that mean so? No. One photon knocks out just one electron. One photon can never knock out two electrons. That's why it's called as one photon, one electron emission. I'll say one photon is enough. One photon is enough to knock out one electron. One photon is enough to knock out one electron. This is something which is very important. This is something which is very, very, very important, right? And my dear students, let me tell you one more important thing. When photon strikes the electron on the metal surface, as soon as it strikes, at the same time, at that point itself, electron is emitted. There is no time lag between striking and emitting. There is no time lag. There is no time lag. Between what? Between striking and emitting. There is no time lag between the striking of the photon and the emission of the electron. Right? Am I clear? Am I clear, people? Am I clear? Am I clear? Am I clear? Quick, quick, quick. Now I have to tell you one more important thing. I need to tell you one more important thing. I need to tell you one more important thing. Tell me, people. Yes, it's instantaneous. Tell me one thing. If I increase the intensity of the light, if I increase the intensity of the light radiation, what is meant by that? I am increasing the intensity of the incident light. That means I'm increasing the number of photons which are going to be incident on the metal surface. Right? I'm increasing the intensity. What does that mean? That means number of photons which are incident on the metal surface, those are increasing. I'm increasing the intensity. That means number of photons which are to be incident on the surface, those I'm increasing. If you are increasing number of photons, you know, one photon is enough to take out one electron. You know, one photon is enough to take out one electron. If you are increasing the photons, that means number of photoelectrons which are emitted, those increases. If number of photoelectrons increases, that means more electrons are leaving the surface. If more electrons are leaving the surface, that means more charge is going in a particular direction. That means more will be the photocurrent. More will be the photocurrent. This is one more very important statement which you have to remember. That means more will be the photocurrent. Now I'm asking you a question. Just answer this. If I increase the intensity of the light, what happens to the kinetic energy of the photoelectron? If I increase the intensity of the light, what happens to the kinetic energy of the photoelectron? Tell me that, quick. Kinetic energy of the photoelectron has nothing to do with the intensity. Kinetic energy of the photoelectron only depends on the frequency of the incident light. Kinetic energy is related to frequency of the incident light. Right? Due to intensity, nothing happens to kinetic energy, nothing happens to stopping potential. Only thing which changes, that is more photoelectrons are emitted, more photocurrent will be there. I'm writing it. Do you remember? On changing the intensity of the incident light, kinetic energy of the photoelectron, stopping potential of the photoelectron remains unchanged. Right? Now if I reverse the statement, on changing the frequency of the incident light, will anything happen to the photocurrent? Photocurrent remains unchanged. Do remember these two statements as well. Now I think you are in a position to make this particular graph. Kinetic energy versus intensity. If you increase the intensity, will anything happen to photocurrent? Sorry, will anything happen to kinetic energy? On increasing the intensity or decreasing the intensity of the incident light, what happens to the kinetic energy of the emitted electrons? Remains unchanged. Am I clear with all these things? Quick. If I'm clear with all these things, let me know the answer of this question, quick. If the work function of the arbitrary metal is 3.1 electron volts. Find its threshold wavelength. Find its threshold wavelength and maximum kinetic energy. Find its threshold wavelength and maximum kinetic energy of the electron emitted when the radiation of 300 nanometer strikes the metal. So radiation of 300 nanometer is striking the metal. That means, what about the incident energy? How much energy is incident? It is hc divided by lambda, right? Since this is in nanometers, so hc value I'm taking as 1240 electron volt nanometer divided by lambda is 300 nanometers. Can you let me know what is this value coming out to be? Can you let me know? It will be 4.13 electron volts. This is the incident energy. This is the incident energy. This is the incident energy, number one. Okay, this is the incident energy, number one. Now, you know, as per photoelectric equation, incident energy is equal to work function plus maximum kinetic energy, right? Incident energy is 4.13 electron volts. Work function is 3.1 electron volts. Can't you calculate the maximum kinetic energy of the photoelectron from here? Tell me the maximum kinetic energy of the photoelectron, quick. 4.1 minus 3.1, which will be almost 1 electron volt. Almost 1 electron volt. Almost 1 electron volt is the maximum. Is the maximum kinetic energy. Almost 1 electron volt, right? What is the next thing? What is the next thing? I need to calculate threshold wavelength. You know, your threshold energy, your work function, that's equal to hc divided by lambda naught, or lambda naught will be equal to hc divided by phi naught. hc divided by phi naught. Since phi naught is given in electron volts, how much? 3.1 electron volts. hc I'll take as 1240 electron volt nanometer. So electron volt cancel. So lambda naught will be equal to 1240 divided by 3.1 nanometers. These were the three things which I was supposed to calculate. Am I clear with all these three things? Am I clear with all these three things? Quick. Am I clear with all these three things? So look at this question. This is your JEE mains question. Look at this question. The work function of certain metals are given. The number of metals which will show photoelectric effect when light of 300 nanometer falls on the metal. If I ask you, how much is the incident energy? hc divided by lambda. hc I'll be using as 1240 electron volt nanometer. What is the incident wavelength, which is 300 nanometer? How much this value comes out to be? EI will be 4.13 electron volts. This is the incident energy. This is the incident energy. This is the energy which is incident on the metal surface, right? The first metal whose work function is 2.4 electron volts. And you are supplying how much? You are supplying how much? You are supplying 4.13 electron volts. Incident energy is greater or equal to work function. So it will show photoelectric effect. Incident energy is greater than work function. It will show. Incident energy is greater than work function. It will show. Incident energy is greater than work function. It will show. Incident energy, which is 4.13, it is less than work function. It won't show. It won't show. It won't show. So how many? 1, 2, 3, 4. So there are 4 metals which will show. There are 4 metals which will show the photoelectric effect. I believe this is again clear to everyone. I believe this is again clear to everyone. Can't you solve this question? Be very quick, short and precise. You have to be very quick, guys. You have to be fast with the calculations. Light of wavelength 400 nanometers. Light of wavelength 400 nanometers. 400 nanometers is incident on the metal whose work function is given 2.3 electron volts. Calculate the stopping potential. Calculate the stopping potential. You know, if lambda is equal to 400 nanometers, can't I calculate the incident energy? hc divided by lambda, which is 1240 electron volt nanometer divided by 400 nanometer. This term cancel. The value will be how much? 3.1. 3.1. This is the incident energy. This is the incident energy. And you already know your incident energy is your work function plus kinetic energy maximum, which can be written as EV naught, which can be written as EV naught, which can be written as EV naught. Sir, what is your marks in +1 chemistry? In my class 11th, I had scored 98 out of 100 in chemistry. Okay? It was 98 out of 100. Okay, quick. Solve it now. Solve it now. What about the incident energy? It is 3.1 electron volts is equal. What about the work function? 2.3 electron volts plus E V naught. Do you see E everywhere cancelling? Yes. So V naught will be equal to 3.1 volt minus 2.3 volt. 3.1 volt minus 2.3 volt. How much this value will be? It is going to be 0.8 volts. This is the stopping potential. This is the reverse voltage which you need to supply. Yes, Malika, you can watch it. Right? Am I clear? In my class 12th, in my chemistry, it was 97 or 99. I don't remember exactly. Yeah? It was, I think, 97 or 99. I don't remember. But class 11th was 98. Class 12th was 97 or 99. I need to check it. I used to be one of the toppers till my 12th. When I entered the college, everything changed. Everything changed. Okay. Perfect. So I believe, people, your photoelectric effect is completely clear. Now it is the time to go into the Bohr's model. Most important topic of this particular chapter, from which questions are going to frequently come. Frequently, right? And my dear students, there are 3 to 4 types of the questions which will be asked in the Bohr's model. Just look at them. All these things you already know them. Bohr's model, it's applicable to single electron species. It is applicable to what? Single electron species, like hydrogen, which carries 1 electron. He positive, carrying 1 electron. Alide positive, it also carries 1 electron. So this Bohr's model, it is valid to only 1 electron species, single electron species. Those species which carry only 1 electron. Number 1. Number 2. As per your Bohr's model, it is again saying the same thing. Atom contains electrons and protons. Atom contains equal number of electrons and protons, due to which atom is neutral. Due to which atom is neutral. Due to which atom is neutral. Okay? Due to which atom is neutral. This is again the same thing which you know. First thing, Bohr's model, it is applicable to single electron species, those species which only contain 1 electron. Number 2, atom contains equal number of electrons and protons, due to which atom is electrically neutral. Electrons are revolving around the nucleus in the circular paths. You call those circular paths as orbits. You call those circular paths which have got constant radius, you call them orbits. Something which is already known, which we know already. Electrons, they revolve around the nucleus in the circular paths, and those circular paths have got fixed radius, right? Those circular paths are something which you call as orbits, right? Those are called as orbits. Now, for the electron to revolve, for the electron to move, for the electron to show the circular path, for the electron to move in the circular path, any object can only move in the circular path if it experiences centripetal force. If it experiences centripetal force, right? Now, since the electron is revolving around the nucleus, so definitely there should be some centripetal force whose direction will be towards the center. There should be some centripetal force whose direction is towards the center. Now, what is that centripetal force? Who is providing that centripetal force? That centripetal force is provided by the electrostatic force of attraction between the nucleus and the electron. Nucleus carries the positive charge, electron carries the negative charge, so there's attraction. So this electron, it experiences the inward force. It experiences the inward force. That inward force is your centripetal force, which is provided by the electrostatic force of attraction. So it is the electrostatic force of attraction which the electron experiences when it revolves around the nucleus. that is providing the necessary centripetal force for the electron to move in the circular path. Right? Now, centripetal force is nothing but mv square divided by r. mv square by r. V is the velocity of electron, r is the radius of the orbit in which electron is moving. What is Fe? Electrostatic force of attraction, which is K Q1 Q2 divided by r square. Divided by r square. Now tell me, imagine that this atom, its atomic number is Z. If its atomic number is Z, that means it contains how many protons? It contains Z protons. It contains Z protons. Let's say one proton carries the charge E. Therefore, Z protons carries the charge plus Ze. Right? So this is the total positive charge of the atom whose atomic number is Z. And this positive charge, it lies inside the nucleus. So inside the nucleus, what is the magnitude of the positive charge? Inside the nucleus, what is the magnitude of the positive charge? It is Ze. What is the charge on electron? It is E. So Q1 is nothing but Ze and Q2 is nothing but E. Q2 is nothing but E, right? So you can write it like this, mv square divided by r is equal to K. What is Q1? Ze. Q2, E. So it is Ze square divided by r square. This is one more result which is important for you. So for the electron to move in the circular path, the electron has to experience the centripetal force. Then only the electron will revolve in the circular path. And that centripetal force is provided by the electrostatic force of attraction between the nucleus and the electron. Right? So the necessary centripetal force which is required for the electron to move in the circular path is provided by the electrostatic force. Right? Am I clear? Am I clear? Now, have you heard about linear momentum? Let's say you've got an object. Its mass is m. Its velocity is v. And this object is showing translational motion. That means the object is moving in a straight line. Right? So there will be linear momentum associated with this particle. What is that linear momentum? Mass of the particle multiplied by velocity of that particle. Now, imagine that you have got an object. Which has got mass m. Which is moving with velocity v. In the circular path. You have got the object which has got mass m, and it's moving with velocity v. If I ask you what is the direction of velocity at this point, draw the tangent. This is the direction of velocity at this point. So this object, it has got mass m, moving with velocity v in the circular path, whose radiuses are. So for this object, I'm not going to define the linear momentum. I'll be defining the angular momentum. For this object. And that angular momentum is nothing but mass multiplied by velocity multiplied by radius. This was linear momentum. This is angular momentum. Linear momentum associated with the particle which shows a translational motion. And here, it is not going to be linear momentum because this is not the translational motion, right? It is what? This is the angular momentum. MVR, it is the angular momentum. Now, my dear students, as per Bohr's model, if this is the nucleus, there are infinite shells. Around the nucleus. Imagine here n is equal to 1. Imagine here n is equal to 2. Here n is equal to 3. N is equal to 4. N is equal to 5. In between, there will be few more shells. In between, there will be infinite shells. As per the Bohr's model, Bohr is concerned, electron can only be present in those shells. In which the orbital angular momentum is the integral multiple of h upon 4 pi. Right? Sorry, h upon 2 pi. Wait. H upon 2 pi. What does that mean? Can you let me know what it means? See, this is your shell number 1. In shell number 1, the angular momentum will be put n is equal to 1. It is going to be h upon 2 pi. In shell number 2, it is 2h upon 2 pi. That means h upon pi. In shell number 3, it is 3h upon 2 pi. In shell number 4, it is 4h upon 2 pi. So electron will be present only in those shells. In these shells, wherein the angular momentum is the integral multiple of h upon 2 pi. Electron won't be present in that shell wherein angular momentum will be 1.1 h upon 2 pi, 1.3 h upon 2 pi, 1.5 h upon 2 pi. You're getting me? There are infinite shells. There are infinite shells here, right? But electron will be only present in those shells wherein the angular momentum is either h upon 2 pi or 2h upon 2 pi, 3h upon 2 pi, 4h upon 2 pi, 5h upon 2 pi. Electron won't be present in that shell wherein the angular momentum will be 1.1 h upon 2 pi, 3.5 h upon 2 pi, right? 4.6 h upon 2 pi. No. No, right? Perfect. And my dear students, there is one more thing. There is one more thing. There is one more thing. When electron, as per Bohr's model, when electron revolves around the nucleus, it neither loses neither it loses energy, nor it gains energy. This is one more important thing as per Bohr's model. When electron revolves around the nucleus, it neither loses nor gains energy. It neither loses nor gains energy, right? So its energy remains constant in a particular orbit. Its energy remains fixed in a particular orbit, right? It neither loses nor gains energy when it revolves around the nucleus, right? Now I'm coming to the main points. When the electron goes from lower energy state to higher energy state, when the electron shifts from lower energy state to higher energy state, energy is absorbed by the electron. Energy is absorbed by the electron. And whenever electron makes a transition from higher energy state to lower energy state, energy is emitted by the electron in the form of radiations. In the form of radiations. Do remember these two things. These are important. For example, the electron is going from this shell number 1, 2, 3. Let's say energy of the first shell is E1, energy of the second shell is E2, energy of the second shell is E3. If I'm saying that electron is going from 1 to 3, that means electron is moving from lower to higher. An electron moves from lower energy state to higher energy state. Energy is absorbed. How much energy is absorbed? Whatever will be the energy gap between these two shells. Whatever will be the energy gap between these two shells, which right now is nothing but E3 minus E1, right? This much energy has to be absorbed by the electron. Then only it goes from 1 to 3. Now, when the electron makes a transition from higher to lower, so from 3 to 1 electron is coming. When electron makes a transition from higher to lower, energy is emitted by the electron. How much energy is emitted by the electron? Whatever it had absorbed before, same amount of energy will be emitted right now, right? Delta E, which is going to be final minus initial. Final minus initial. It is just the delta E value here will be positive and delta E value here will be negative, right? This positive value tells you that energy is absorbed by the electron, and this negative value tells you that energy is emitted by the electron. Positive value tells you that energy is absorbed, and negative value tells you energy is emitted by the electron. Right? Perfect. So when the electron makes a transition from lower to higher, energy is absorbed by the electron. How much? Whatever is the energy gap between those two shells. When electron makes a transition from higher to lower, energy is emitted by the electron. How much? Whatever will be the energy gap between those two shells. Right? Now the main things in this particular model, what is that? What is that? My dear students, this is something which is important. The question which you get, how to calculate radius of the nth Bohr's orbit. How do we calculate the radius of nth Bohr's orbit? Do remember the results directly. I'm not deriving any result here. Just remember them and let's try to apply them. Let's say this is the nucleus. Let's say this is the nucleus. Let's say the electron is present in this nth shell. I'm calling this as nth shell, nth orbit. Let's say the atomic number of the atom is Z. Atomic number of the atom is Z, right? If I need to calculate this radius, which I'm representing with Rn, so radius of nth Bohr's orbit is equal to R naught n square divided by Z. R naught n square divided by Z. R naught n square divided by Z. R naught is nothing but 0.529 angstroms. Number one. Number two, people. Number two. Whenever you need to compare the radii of two Bohr's orbits, it's going to be what? It will be R1 divided by R2 is equal to N1 square divided by N2 square. This is going to be Z2 and this is going to be Z1, right? This is how you compare the radius of nth Bohr's, the radius of two Bohr's orbits. Perfect. Now guys, can we plot some graphs here? Try to understand, can we plot some graphs here related to radius? My dear students, case 1 related to graphs. Imagine Z is constant. Imagine Z is constant. If Z is constant, I can plot two graphs here. One graph will be radius of the nth Bohr's orbit versus n. Second graph is going to be radius of nth Bohr's orbit versus n square. I can plot these two graphs. How exactly? Try to have a look. You know, radius of nth Bohr's orbit is equal to R naught n square divided by Z. Z is constant. Now, this particular graph, radius of nth Bohr's orbit, you are plotting along y-axis. N square, complete n square, you are plotting along x-axis, right? This R naught by Z is your m. Y is equal to mx. Let me write it like this. Radius of nth Bohr's orbit is equal to R naught divided by Z, n square. Rn, you are plotting along y-axis, n square along x-axis. So this becomes your m. Y is equal to mx, means straight line with a positive slope. If I ask you what about the slope of this curve, slope will be nothing but R naught divided by Z. Right? Now, Rn versus n. So look at this scenario again. Rn, you are plotting along y-axis. N, you are plotting along y-axis. N, you are plotting along x-axis. So instead of n, I'll write x, right? So this n ka square, so x ka square. Y is equal to kx square. Means parabola opening upwards. Simple people. Is it simple? This was case 1 in radius. Now, case 2 in radius. What is the case 2 in radius? Look here. Second graph. If, for example, if n is constant, which clearly tells you n square will be also constant. Imagine this n is constant. If n is constant, n square is also constant, right? Okay. So my result becomes Rn is equal to R naught divided by Z multiplied by n square. Now, for example, I need to plot a graph. Right now between radius of nth Bohr's orbit versus Z. Or let's say I'm plotting a graph between radius of nth Bohr's orbit versus 1 upon Z. Can you make these graphs for me? Quick. You have to be very quick, guys. Radius of nth Bohr's orbit versus Z. R versus Z. Both are inversely proportional. Whenever you need to plot a graph between two variables, which are inversely proportional to each other, the nature of the curve is rectangular hyperbola. So this is your hyperbola. Right? Now, Rn versus 1 upon Z. So you can write the same equation like this. Rn is equal to R naught n square 1 upon Z. Over here, 1 upon Z you are plotting along x-axis. This you are plotting along y-axis. Now have a look, people. 1 upon Z you are plotting along x-axis. Rn you are plotting along y-axis. This entire thing becomes your m. So y is equal to mx is a straight line. What about the slope of it? It will be R naught n square. This is going to be the slope of this graph. Just say yes or no in the chats if it is clear. So these were the things which you have to remember related to what? Related to your radius of nth Bohr's orbit. These 4 graphs and these 2 equations. That's all. Right? Second thing which we can get from the Bohr's model. What is that? That is the velocity. Of the electron in nth Bohr's orbit. Velocity of the electron in the nth Bohr's orbit. How do we calculate velocity of the electron in the nth Bohr's orbit, which I'm representing with Vn? My dear students, a direct result I'm giving. Velocity of the electron in the nth Bohr's orbit is equal to V naught Z divided by N. Now you must be thinking what this V naught is. V naught is a constant whose value is 2.18 into 10 raised power 6 meter per second. This is your V naught. Remember directly. Whenever you need to compare the velocities of two electrons, so V1 divided by V2 is equal to Z1 upon Z2 multiplied by N2 divided by N1. n2 divided by n1, right? Now, case 1. If, for example, n is constant, if, for example, n is constant, can you plot a graph? Can you plot a graph between velocity of electron in the nth Bohr's orbit versus z? You can do that. N is constant. N is constant. This is y. This is x. So this becomes your m. Y is equal to mx means straight line passing through origin. Its slope will be nothing but v naught divided by n. Its slope will be nothing but v naught divided by n. Guys, are you understanding how this graph I'm making? This was the equation. Vn is equal to v naught z divided by n. Vn you are plotting along y-axis. Z you are plotting along x-axis. So this becomes your m. Y is equal to mx. Khatam. Right? Similarly, second graph which you can get over here. Imagine z is constant. Imagine z is constant. So here you can plot two graphs. One is your velocity of electron in nth Bohr's orbit versus n. And second one was your velocity of the electron in the nth Bohr's orbit versus 1 upon n. Can you make both the graphs? Can you make both the graphs, people? Be very specific, be very quick. See, your direct result is Vn is equal to V naught Z divided by n. Right? Z divided by n. Vn you are plotting along y-axis. N you are plotting along x-axis. Vn versus n. Two variables inversely proportional to each other. Two variables inversely proportional to each other. Hyperbola. Right? Hyperbola. Vn versus 1 upon n. Vn versus 1 upon n. Now tell me one thing. Vn versus 1 upon n. Can't I write it like this? V naught Z multiplied by 1 upon n. So Vn you are plotting along y-axis. 1 upon n you are plotting along x-axis. So this becomes your m. Y is equal to mx straight line. What about its slope? Its slope is V naught multiplied by Z. Am I clear? Am I clear, people? Am I clear? Am I clear? Only these things you have to remember about the velocity. About the velocity. Moving ahead. The third question which will be asked from here. Time period. How do we calculate time period of the electron? Which you are representing with Tn. How you guys are going to calculate time period of the electron? Direct result I'm giving, okay? Time period of the electron in the nth Bohr's orbit is equal to T naught n cube upon z square. T naught n cube upon z square. Remember directly. What is meant by time period of electron? Time taken to complete one revolution. Time taken to complete one revolution. Right? If I ask you what will be the value of T naught value will be 1.6 into 10 raised power minus 16 seconds. This is the value of your T naught. This is the value of your T naught. Now, my dear students, one more thing. Whenever you need to compare the time period of two electrons, how you are going to do that? T1 divided by T2 is equal to N1 cube divided by N2 cube. This will be Z2 ka square. This will be Z1 ka square. This is how you compare the time periods of the two electrons in two different orbits. Right? And similarly, my dear students, if they ask you about frequency, if they ask you about the frequency of the electron in the nth Bohr's orbit, how exactly you are going to do it? How do you calculate frequency? Frequency is nothing but inverse of time period. Right? If this was directly proportional to n cube, inversely proportional to z square. So frequency of electron in the nth Bohr's orbit will be directly proportional to z square, inversely proportional to n cube. Right? If you want to compare the frequencies, V1 by V2 is equal to Z1 square. This is Z2 square. This is N2 cube. And this is N1 cube. Perfect. These are few results which you need to remember directly. Right? And I believe you can plot any of the graphs, whatever is asked. Okay? Now, is this it? No. There are a few more things. Number 4. Total energy possessed by the electron in the nth orbit. Let me write it first like this. Total energy possessed by the electron in the nth orbit, which will be the sum of kinetic energy of the electron and the potential energy possessed. total energy possessed by the electron is equal to the sum of kinetic and potential. The sum of kinetic and potential. So kinetic energy formula, directly remember, plus 13.6 Z square divided by N square electron volts. Potential energy formula, minus 27.2 Z square divided by N square electron volts. Total energy formula, this plus this, which makes it minus 13.6 Z square upon N square electron volts. These are three results which you need to remember. These are three results which you need to remember. One is related to total energy of the electron, potential energy, and the kinetic energy. Am I clear? Am I clear, people? Am I clear? Let me know in the chats quickly. Am I clear with all these things? Quick, quick, quick. Everyone. 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 Am I clear? Am I clear? Perfect. Right? Perfect, guys. Perfect, perfect. So I believe all these results are clear. Now there are some things which are very important, which you need to know. Or before doing those things, let's try to solve few basic questions which will make your things clear. Can't you solve this question, this basic question, people? Can't you solve this question? Calculate the radius ratio of the second orbit of He positive, and third orbit of Be tripositive. Let me call this as number 1. Let me call this as number 2. Right? Okay. Second orbit, they are talking about second orbit of He positive. What is the atomic number of helium? Hydrogen, helium. Right? Let's say the radius of the second orbit of He positive is R1. Okay. Now here, we need to compare it with the third orbit here. So N2 is 3. Hydrogen, helium, lithium, beryllium. Right? Let's say the radius here is R2. And already you know, R1 divided by R2 is equal to R naught N square by Z, right? N1 square divided by N2 square multiplied by Z2 divided by Z1. N1 square is 2 ka square 4. N2 square is 3 ka square 9. Z2 is your 4. Z1 is your 2. Right? So the value comes out to be 16 divided by 18. Or did I do any mistake here? Just a second. This is 2. 2 ka square is 4. Right? N2 was 3. 3 ka square is 9. Z2 is 2. Z2 is 4. And Z1 is 2. Right? 4, 4, 69 to 8. 16 is to 18. Right? 8 is to 9. 8 is to 9 is the correct answer of the question. Done and dusted. Right? Okay. Look at this one. If the velocity of the electron in the first orbit of hydrogen, is V, what is the atomic number of hydrogen? That is 1. What will be the velocity of the electron in third orbit of Li dipositive? In the third orbit of Li dipositive. Third orbit. Right? Third orbit. Hydrogen, helium, lithium. Velocity of electron in the first orbit. N1 here was 1. Can't you solve this? Can't you solve this, people? Can't you solve this? You know it already. V1 divided by V2 is equal to V is equal to V naught Z by N. Right? So this is Z1 by Z2 multiplied by N2 divided by N1. V1 is nothing but V. V2 we have to calculate. Z1 is 1. Z2 is 3, N2 is 3, and N1 is 1. So V is equal to V2. This is something which is the answer of the question. As simple as that. Right? I believe I'm clear. I believe I'm clear to everyone, guys. I believe I'm clear to everyone. Okay? Perfect. Now, guys, one quick statement. You know the total energy possessed by the electron in the nth Bohr's orbit is minus 13.6 z square upon n square. Correct? Tell me one thing. If n increases, if shell number increases, if electron goes far from the nucleus, if n increases, that means z square divided by n square value, it will decrease. Z square by n square value will decrease, right? Which tells you that 13.6 z square upon n square value will also decrease, right? Or if I multiply this with minus sign, so minus 13.6 z square divided by n square, this whole term will increase. What does that mean? That means energy of the electron is increasing. So one statement which you need to generalize from here, when you increase n, when electron goes far from the nucleus, energy of the electron increases. In short, as the electron goes far, energy possessed by the electron, energy of the electron, what happens to that? That increases. That increases. Am I clear? One more thing. If z value increases, this term increases and overall term decreases. If z increases, that means energy, what happens to that? That decreases. Correct? Because there's a minus sign here. Correct? Am I clear? With all these things? The important one is this one. As the electron goes far from the nucleus, energy of the electron increases. That's all. That is all. If I'm clear, let me know once in the chats. If I'm clear, let me know once in the chats. If I'm clear, let me know once in the chats. Then only I can move ahead. Yes? Then only I can move ahead. Z is atomic number. Let me know quickly in the chats, people, if all the things are super clear till now. Few more things which I want to discuss with you. Graphs related to energy. Energy of the nth Bohr's orbit is equal to minus 13.6 z square divided by n square electron volts. You know it already, right? Now, for example, first thing, imagine if n is constant. If n is constant, that means n square is also constant. Right? For example, I want to plot a graph. First graph I want to plot between energy of the electron in the nth Bohr's orbit versus z. The second graph which I want to plot, that is going to be energy of the nth Bohr's orbit versus z square. Can you let me know the nature of the curves? You know, energy of the nth Bohr's orbit is equal to minus 13.6 z square divided by n square. See, n is constant, so n square is also constant. So I can write it like this. En is equal to minus 13.6 divided by n square, and this is z square. Now, in the first case, you are plotting En along y-axis, this along x-axis. So instead of En, you can write y. Instead of z, you can write x. But this is z ka square, so this x ka square. This becomes your m. Right? So y is equal to kx square. Y is equal to mx square. Y is y is equal to mx square or y is equal to kx square. It has to be parabola opening upwards, right? It has to be parabola opening upwards because y is equal to kx square format is there. But there's a minus sign here. Minus sign means just remove it. Minus sign means just remove it and take the reflection along this side. The graph will be like this. The graph will be like this. Is this clear? Because there's a minus sign in the beginning. There's a minus sign in the beginning. Okay, En versus Z square. En versus Z square. Over here, En you are plotting along y-axis. Z square you are plotting along x-axis. So this is your y. Instead of whole Z square you are writing x. And this is your m. Y is equal to mx means straight line. But there's a negative sign. So that straight line has to be in the fourth quadrant. Right? That straight line has to be in the fourth quadrant. Is it clear? Is it clear? So this was your case 1. Now, looking at case 2. Looking at case 2. If, for example, Z is constant. If Z is constant, that tells you Z square is also constant. That tells you Z square is also constant. Right? Now, for example, I'm plotting a graph between En versus n square. En versus n square. En versus n square. En and n square, they are inversely proportional. Inversely proportional means hyperbola. So hyperbola is like this. But there is a minus sign. So that hyperbola will be in this quadrant. Right? Because there is a minus sign in the beginning. Right? I believe all these things are clear. I believe all these things are absolutely clear to everyone. And my dear students, as I told you, as the value of n increases, the energy of the electron increases. The energy of the electron increases. Now there is something which is very important. If I particularly talk about hydrogen atom, look at this diagram very carefully. I'm talking about hydrogen atom. If I'm talking about hydrogen atom, your Z value is 1 for hydrogen. Your Z value is 1 for hydrogen, right? Do you know how do we calculate energy of the electron in the nth Bohr's orbit? It is equal to minus 13.6 Z square upon n square electron volts, right? In case of hydrogen atom, this is your hydrogen's nucleus. This is shell number 1, this is shell number 2, this is shell number 3, right? This is 1, this is 2, this is 3. If the electron is here, how much energy it carries? Since it is hydrogen, so Z is already 1 and N is here 1. Z1, N1. So energy of electron in the first orbit of hydrogen. Energy of electron in the first orbit of hydrogen, right? This line represents your first orbit of hydrogen, right? Energy of electron in the first orbit is minus 13.6. If you use the same result and calculate the energy of electron in the second orbit of hydrogen, you just have to put the value of N as 2. The value will be minus 3.4 electron volts, right? Energy of the electron in the third orbit is this fourth orbit, this, right? Infinity. Put N as infinity. That means electron is at infinite distance from the nucleus. Electron is at infinite distance from the nucleus. Put N as infinity. If you put N as infinity, this term becomes 0. So energy of electron here comes out to be 0. If you look carefully, energy of electron in the first shell is minus 13.6. Second, minus 3.4. Third, minus 1.5. So, as the electron is going far from the nucleus, is the energy of electron increasing? Yes, energy of electron is increasing. Can I say this is the maximum energy of the electron? Yes, this is the maximum energy of electron. This is the maximum energy of electron. Now, the sign here is negative. Here also negative. Here also negative. Here also negative. The sign of energy possessed by the electron is negative. What does it mean? What does it indicate? It means that the negative sign of energy, it indicates that your electron is under the influence of nucleus. Is under the influence of nucleus. It is under the influence of nucleus. Here the value of energy is 0. That means electron is present in the infinite shell. What does that mean? Infinite shell. That means distance between electron and nucleus is infinity. So there will be no force of attraction between the nucleus and the electron when electron is present at the infinite shell. So that means electron is out of the influence of the nucleus. If the electron is present in shell number 1, that means nucleus will be attracting electron at that time. Shell number 2, nucleus is still attracting electron. Shell number 3, nucleus is still attracting electron. Shell number infinite. Now nucleus is not attracting that electron. That electron is out of the influence of the nucleus. That electron is out of the influence of the nucleus. That means you have taken the electron out from the atom. That means you have taken the electron out from the atom. Am I clear with this? Am I clear with this? Correct? So from now onwards, if I tell you something like this, I'm telling you, take the electron out of the atom. Take the electron out from the atom. What does that mean? That means you have to send the electron to n is equal to infinity. You have to send the electron to n is equal to infinity. Yeah? That means you have to send the electron to n is equal to infinity. Then only I can say electron is out of the influence of the nucleus. Okay? And one more thing. Shell number 1, n is equal to 1 is called as ground state. N is equal to 2, second shell. It is called as first excited state. N is equal to 3, second excited state. N is equal to 4, third excited state. And guys, there is one more thing. Look at the energy gap between these two. How do we get the energy gap between these two shells? This minus this. This minus this gives you energy gap between these two, right? This minus this gives you energy gap between these two. Similarly, this minus this, it will give me the energy gap between these two, right? If you look carefully, the energy gap between 1 and 2 and energy gap between 2 and 3, is it same? It is not same. 10.2 electron volts, 1.89 electron volts. Here it will be less. So as you go far from the nucleus, the energy gap between the two consecutive shells, that decreases. It is simply like this. If this is nucleus, this is the first shell. Here you will be the second shell. Third shell is comparatively closer. Fourth shell is comparatively closer. Fifth shell is comparatively more closer. You getting it? As you move far from the nucleus, the energy gap between the two consecutive shells, it keeps on decreasing. Yeah? Perfect? Perfect, people? Am I clear? 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 Look at this point. Ionization energy. Ionization energy. Everyone would be knowing about ionization energy. How do you define the ionization energy? How do you define the ionization energy? The energy which is required. The energy which is required to remove the electron from the valence shell of that. The amount of energy which is required to remove the electron from the valence shell of that. In case of hydrogen, how many electrons are there? 1 electron, right? That 1 electron in hydrogen will be present in the first shell only, right? The amount of energy which is required to remove the valence shell, to remove the valence electron, it is basically from an isolated gaseous atom. It is basically from an isolated gaseous atom. Leave that part aside. I'm talking about something else. If you look at the definition of ionization energy, it is the amount of energy which is required to remove the valence electron from that. To remove the valence electron. If I talk about hydrogen, in hydrogen there is 1 electron, and then that 1 electron is in shell number 1. I'm telling you, define the ionization energy for hydrogen. That means I'm asking you, calculate the energy which is required to remove this electron. To remove this electron, because this is the valence electron of hydrogen. It contains only 1 electron. Hydrogen contains only 1 electron. So this is the valence electron of hydrogen. I'm telling you to remove this valence electron. Remove this valence electron, matlab, I want you guys to take this electron from this n is equal to 1 to n is equal to infinity. Right? Because when you shift it from n is equal to 1 to n is equal to infinity, when you shift it from n is equal to 1 to n is equal to infinity, then only at infinity, electron will be out of the influence of the nucleus. That means you have taken the electron out. Now, if you look carefully, you are sending the electron from lower energy state to higher energy state. Energy has to be absorbed with the electron. And that amount of energy which is absorbed with the electron here will be equal final minus initial, A infinite minus E1, A infinite minus E1. And this energy gap, this delta E, this much amount of energy has to be absorbed by the electron, then only it will shift from 1 to infinity, right? And the amount of energy required is something which is what you call as ionization energy here, right? So if you want to get the expression of ionization energy, it is A infinite 0 minus E1. E1 is minus 13.6 Z square upon N square, right? For since I'm talking about hydrogen, Z is 1, N is 1. So it is just 13.6 electron volts. So this is the ionization energy of hydrogen. This is the ionization energy of hydrogen. For all the hydrogen-like atoms, your ionization energy will be equal, when you calculate it, it will be plus 13.6 Z square electron volts. This is for all the hydrogen-like atoms. This is particularly for hydrogen, right? This is particularly for hydrogen. This is hydrogen-like species. This much amount of energy is required to send the electron from the valence shell of hydrogen to infinity. So this is the basically ionization energy which is defined for hydrogen, right? If you look carefully, what is the ionization energy of hydrogen? 13.6. What is the energy of electron in the first shell of hydrogen? That was minus 13.6. So can I say ionization energy is nothing but it is the minus times the energy of N is equal to 1, right? Energy of N is equal to 1. Can I say something like this? If you look carefully, this is the ionization energy of hydrogen, and energy of electron in the first shell of hydrogen was minus 13.6. So this has to be the relation between the two. Okay. Now guys, try to define binding energy. Ionization energy formula is 13.6 Z square electron volts, right? 13.6 Z square electron volts. That is the ionization energy formula. Ionization energy means the amount of energy required to take the electron from the valence shell to N is equal to infinite. Look at the binding energy. The energy required to remove the electron from a given energy state. For example, this is the nucleus. Right? This is the nucleus. This is shell number 1, this is shell number 2, this is here shell number N. Right? The electron is present in the nth energy state. I want to take this electron out. See, this electron right now is being attracted by the nucleus. It is being attracted by the nucleus. Now I want to take this electron out. I want to make sure this electron goes out of the influence of the nucleus. That means I have to send this electron to infinite shell. That means I have to send the electron from here to here. And in order to send the electron from lower energy state to higher energy state, energy absorbed. How much energy is absorbed? Delta E, which will be E final minus E initial. This is E final minus E initial. Correct? This is something which you call as binding energy. So binding energy formula becomes what? E infinite is 0, and energy of electron in the nth energy state is minus 13.6 N square by Z square minus plus 13.6 Z square upon N square electron volt. So this is the formula to calculate the binding energy from a given energy state to infinite shell. Right? Now, if N is equal to 1, binding energy becomes 13.6 Z square. Right? 13.6 Z square was ionization energy for any hydrogen-like atom. So can I say your binding energy and ionization energy becomes equal when N is equal to 1? When the given energy state is 1? Sir, what about game of NEET? This is game of NEET only going on, right? It is just the name of the series is changed. Study from here. Guys, am I clear? This is your binding energy. If N is 1, binding energy is equal to 13.6 Z square, which was ionization energy for hydrogen-like species. So ionization energy and binding energy, they are equal when N is equal to 1. Okay? Have you heard about excitation energy? Say, for example, this is the nucleus. The electron is present in shell number N1 and it has to go from N1 to N2. Now, from N1 to N2, lower energy state to higher energy state, energy is required. The energy which is required to excite the electron from lower energy state to higher energy state, right? That's something which you call as excitation energy. So what is excitation energy? When you want to send the electron from lower energy state to higher energy state, right? That amount of energy required, which will be equal delta E, which will be equal delta E, which will be final minus initial, E of N2 minus E of N1, right? So excitation energy has to be equal. This will be minus 13.6 Z square upon N2 square minus, this will be minus 13.6 Z square upon N1 square. So here your excitation energy result becomes 13.6 Z square 1 upon N1 square minus 1 upon N2 square. This is how you calculate your excitation energy. This is how you calculate excitation energy. I hope this is clear to everyone, right? I hope this is clear to everyone. The amount of energy which is required, to make sure that electron goes from lower energy state to higher energy state. That's all. That's all. Okay? My dear students, can you try to solve this particular question? Just try to solve. Radiation corresponding to n is equal to 4. Radiation corresponding to transition n is equal to 4 to n is equal to 2 in hydrogen falls on the matter of work function 2.5 electron volts. The maximum kinetic energy of the photoelectron. Look at this question carefully. Imagine this your n is equal to 2. Imagine this n is equal to 4. Electron is moving from 4 to 2. Electron is going from 4 to 2. Higher energy state to lower energy state. So energy will be released. How much energy will be released? How much energy will be released? Delta E. Delta E. How much that's going to be? Are we talking about hydrogen? Yes, we are talking about hydrogen. Yes, we are talking about hydrogen. We are talking about hydrogen. Right? So, energy of the electron in the fourth energy state is minus 13.6. Z square will be 1. N square. 4 ka square is 16. Right? N is equal to 2. E2 will be equal to minus 13.6. Z is 1 for hydrogen. Divided by N square. 2 ka square is 4 electron volts. Perfect. How much energy will be released when electron makes a transition from 4 to 1? From 4 to 1, right? From 4 to 1. Let me check how much energy is there in fourth energy state. Just a second. Energy of the electron in the fourth energy state of hydrogen is 0.85, minus 0.85. So it is minus 0.85 here. This is E4 is equal to minus 0.85 here, electron volts. Similarly, E2. How much was E2 value? Minus 3.4, right? E2 was minus 3.4. Energy of the electron in the second orbit is minus 3.4. You can calculate it to minus 3.4 electron volts, right? Perfect. Now, when the electron goes from 4 to 2, energy is released. How much? Whatever is the energy gap. Energy gap here will be E2 minus E4. What is E2? What is E2? Minus 3.4. What is E4? Minus 0.85. Minus 0.85. How much this value will be? Minus 3.4 plus 0.85. Right? How much this value will be? 5. Right? 13 minus 8. 5. It will be minus 2.55 electron volts. This minus only signifies that energy is released. This minus only signifies here the energy is released. Now, when the electron is going from 4 to 2, energy is released. How much? 2.55 electron volts. Now, this much amount of energy which is released, it is falling on the metal whose work function is 2.5. It is falling on the metal whose work function is... What is happening here? It is falling on the metal whose work function is 2.5 electron volts. Okay? This much amount of energy. How much? How much? 2.5 electron volts of energy is falling on the metal whose work function is 2.5 electron volts. The maximum kinetic energy. EI is equal to 5 plus kinetic energy max. So from here, you can calculate the maximum kinetic energy of the photoelectron, which will be 2.55 minus 2.5, which will be 0.05 electron volts. Is this clear? Is this clear, guys? Is this clear? Is it clear to everyone? I hope so. Right? I hope so. Now guys, let me tell you one more thing. There is one more question asked. What is that? That is calculation of wavelength absorbed or released. Calculation of wavelength absorbed or released when electron makes a transition between two energy states. When electron makes a transition between two energy states. Between two energy states. When electron makes a transition between two energy states. What does that mean? See guys, it's very simple. You know, when the electron makes a transition from higher energy state to lower energy state, it emits energy in the form of radiation. It emits energy in the form of radiation. That radiation will be having certain wavelength. That radiation will have certain wavelength, right? Correct? Similarly, when electron makes a transition from lower to higher, energy is absorbed by the electron in the form of radiation. That radiation again has got wavelength. How do we calculate? How do we calculate the wavelength of the radiation emitted or absorbed during the transition? Right? Again, I'm telling you the same thing. Understand. When electron makes a transition from higher energy state to lower energy state, it emits energy in the form of radiation. That radiation will have certain wavelength. Right? Similarly, when electron makes a transition from lower to higher, energy is absorbed by the electron, right, in the form of radiation. That radiation will have wavelength. How do we calculate the wavelength of the radiation emitted or absorbed during the transition? For that, you have got a formula. 1 divided by lambda is equal to Rz square upon 1 upon n1 square minus 1 upon n2 square. This 1 by lambda is something which you call as wave number. This formula over here is used to calculate the wavelength of the radiation emitted or absorbed during a transition. Okay? This formula is something which you call as Rydberg's formula. You call this as Rydberg's formula. And over here, R is a Rydberg's constant. Do remember 1 by R is equal to 911.5 angstroms. Do remember 1 by R is equal to 911.5 angstroms. And at the same time, do remember N1 here represents your lower energy state and N2 represents your higher energy state. N1 represents your lower energy state, N2 represents your higher energy state. Right? Perfect. Now, my dear students, if you look carefully, I'm pretty much sure every one of you would have heard about hydrogen spectrum. Every one of you would have heard about hydrogen spectrum. Let me show you some important things, because this is something which is very, very, very important and crucial, right? From which question comes? From which question comes? All right, look here, people. Try to understand. This is your ground state, n is equal to 1. First excited state, second excited state, third excited state, fourth excited state, fifth excited state, sixth excited state, right? Okay. Now, you know, I'm talking about hydrogen atom. You know, when the electron moves from lower energy state to higher energy state, energy is absorbed. You know that. And when the electron reaches the higher energy state, it just resides there for 10 raised power minus 8 seconds. When the electron moves from lower energy state to higher energy state. When the electron moves from lower energy state to higher energy state. At higher energy state, electron is unstable. So it jumps back. It jumps back to the lower energy state. It jumps back from higher to lower. And when the electron jumps back from higher to lower, it will emit energy in the form of radiations. It will emit energy in the form of radiations, right? And my dear students, when electron makes a transition, from higher energy state to shell number 1, from higher energy state to shell number 1, from higher energy state to shell number 1, from higher energy state to shell number 1. The series of lines which we get over here, you call them as Lyman series. So what is Lyman series? When the electron makes a transition from higher energy state to shell number 1, the series of radiations which we get, you got a series of radiations over here, which have got different wavelengths. These series of radiations is what you call as Lyman series. Similarly, when the electron makes a transition from higher energy state to shell number 2, from higher energy state to shell number 2, from higher energy state to shell number 2, higher energy state to shell number 2, right? The series of lines which we get over here, this series of lines is something which you call as Balmer series. When the electron makes a transition from higher energy state to shell number 3, from higher energy state to shell number 3, from higher energy state to shell number 3, the series of lines obtained is what you call as Paschen series, right? Higher energy state to shell number 4, higher energy state to shell number 4. This is your bracket series. Higher energy state to shell number 5. This is called as Fund series. Similarly, higher energy state to shell number 6. Humphrey series. Humphrey series. Humphrey series. Lyman, Balmer, Paschen, bracket, Fund, Humphrey. Okay, tell me one thing. We are talking about hydrogen spectrum, right? See, if you look at the Lyman series, in the Lyman series, the electron makes a transition from higher energy state to shell number 1, right? Higher energy state to shell number 1. Then the electron will be making a transition from 2 to 1. This line, this line, either you call it as the first line of Lyman series, or you call it as H alpha line of Lyman. Similarly, this particular line, when the electron is making from 3 to 1, it is either called as second line of Lyman series, or you call it as H beta line. Similarly, this particular line, third line or H gamma line. Similarly, this particular line is what I call as first line of Balmer series. First line of Balmer series or H alpha line of Balmer. Right? Similarly, this is second line or H beta line of Balmer. Okay? This is first line of Paschen or H alpha line. Second line of Paschen. First line of bracket. Second line of bracket. Right? H alpha, H beta. Okay? Now guys, if you look at the Lyman series carefully, if I particularly want to analyze the Lyman series, if I want to analyze the Lyman series, in the Lyman series, the electron makes a transition from higher energy state to shell number 1. Higher energy state to shell number 1, right? If I ask you to calculate the shortest wavelength in Lyman series, shortest wavelength emitted in case of Lyman series, shortest wavelength. See, we know in case of a Lyman series, electron makes a transition from higher to shell number 1. When the electron makes a transition from higher to lower, energy is emitted in the form of radiation. That radiation will be having certain wavelength, right? I need to calculate what is the shortest possible wavelength in case of Lyman series. Shortest wavelength. Shortest wavelength is also called as series limit. Sometimes they might confuse you in the question. They'll ask you to calculate the series limit. It'll ask you to calculate the series limit. Series limit means shortest wavelength. Shortest wavelength in Lyman series. Shortest wavelength, you know, delta E is inversely proportional to lambda, right? So if this has to be shortest, this has to be, if this has to be shortest, this has to be maximum. So for the shortest wavelength, delta E energy gap has to be maximum. For the shortest wavelength, energy gap has to be maximum, right? Now, in the Lyman series, where do you see the energy gap maximum? 2 to 1, 3 to 1, 4 to 1, 5 to 1, or infinity to 1? Energy gap is maximum when the electron is making a transition from infinity to 1. You know, your lower energy state here is N1, your higher energy state here is N2, right? Now, you can use the Rydberg's formula. 1 divided by lambda is equal to R Z square 1 upon N1 square minus 1 upon N2 square, right? So 1 divided by, we are supposed to calculate the minimum wavelength. So R I'm writing as such, Z for hydrogen is 1, 1 upon N1 square. 1 ka square is 1 only, minus 1 upon infinity. Perfect. So 1 upon lambda minimum is nothing but, it will be R, right? Or lambda minimum will be equal to 1 divided by R. And you know 1 by R value is nothing but 911.5 angstroms. Right? So this is something which I call as the minimum wavelength, shortest wavelength, or the series limit in case of Lyman series. In case of Lyman series. In case of Lyman series. Am I clear? In case of Lyman series only, if they ask you about the longest wavelength, calculate the longest wavelength in case of Lyman series. So lambda max they are asking, for example, longest wavelength in case of Lyman. Longest wavelength in case of Lyman. Longest wavelength means, since you know delta E is inversely proportional to lambda. If this has to be longest, this has to be minimum. Now, which one is the minimum energy gap in Lyman? 2 to 1, 3 to 1, 4 to 1, which one? It is 2 to 1, which is the minimum energy gap in Lyman. Minimum energy gap in Lyman means electron is making a transition from 2 to 1. Lower energy state is N1, higher energy state is N2, right? So 1 divided by lambda max will be equal to R, Z square is 1, 1 upon N1 square minus 1 upon N2 square, right? So it's going to be 1 upon lambda maximum, which will be equal 4 minus 1, 3. So 3 divided by 4R. So here you can calculate lambda maximum, which is going to be 4 divided by 3 multiplied by 1 by R. 1 by R is nothing but 911.5. And the units are going to be in angstroms. So this is what you call as maximum wavelength emitted. In what? In your Lyman series. Same things you can do for all the other series. Balmer, Paschen, bracket fund, right? Minimum and maximum, everywhere. Okay, I'm asking you a question. If you are supposed to calculate the shortest wavelength in Balmer series, can you tell me the transition? Shortest wavelength in Balmer series. Tell me the transition. From where to where electron has to go? Shortest wavelength in Balmer. Can you tell me the transition? Shortest wavelength in Balmer. Quick. Shortest wavelength in Balmer. Shortest means maximum energy gap. Maximum energy gap in Balmer is infinity to 2. Right? Vijay, don't ask the irrelevant questions. I'm asking something different, and you're asking me, where is Pankuri ma'am? How do I know where is she? You can ask her. Why are you asking me? I'm teaching something important. You're telling me where is this, where is that? Just ask that person where she is. Am I clear with all these things? Again, you'll ask the same thing. I'm sorry. I need to block you. Perfect. All clear? All right. I hope these sort of questions you can easily solve from now on. Guys, and look at this particular table as well. From this table, question has been coming. Your Lyman series. What is a Lyman series? It's a series of radiations when electron makes a transition from higher to n is equal to 1. Right? It's a series of radiations which we get. Those radiations have got different wavelengths. all the radiations in the Lyman series, they fall in ultraviolet region. They fall in ultraviolet region. All the radiations which we get in Balmer series, they fall in visible, infrared, 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 infrared. You can remember it like this: UV, I, ultraviolet, visible, infra, infra, far infra, far infra. Right? There was a question asked in NEET 2 years back. In which region your Balmer series falls? Balmer series falls under visible category. So all the radiations which we get in Balmer series, you can see them by your eyes. You can see them by your eyes. Okay? Remember it. Remember it. Can you give this question a try quick? Give this question a try. Give this question a try. And guys, after this, we'll take a break for 20-25 minutes. We'll have dinner and come back, okay? Because this chapter will further take 2 more hours. 2 more hours it might take. Let's see. What transition in hydrogen spectrum? What transition in hydrogen spectrum would have same wavelength as the Balmer transition n is equal to 4 to n is equal to 2 in case of He positive? So in case of He positive, electron is making a transition from 4 to 2. Lower energy state is N1, higher energy state is N2. Right? Electron is making a transition from 4 to 2 in case of He positive. So it will be emitting some radiation which will have certain wavelength. Now in hydrogen, what should be the transition so that the wavelength emitted is same? Let's say the transition here is from N2 to N1. Let's say the transition here is from N2 to N1. Okay? So I can say 1 divided by lambda is equal to R. Z square is 1. 1 upon N1 square minus 1 upon N2 square. Okay? Here it's going to be 1 divided by lambda is equal to R. Z square. For helium, Z is 2. 2 square is 4. Right? 1 upon N1 square minus N2 square. Correct? It can be 1 divided by lambda is equal to this 4 got cancelled. 4, 1, 4, 4. So it's R 1 divided by 1 minus 1 divided by 4. Or you can say 1 divided by lambda is equal to R. It's going to be 1 upon 1 ka square minus 1 upon 2 ka square. Correct? Dear students, if you just equate these two, if you just relate these two, if you compare these two, get the N1 and N2 value from here. If you compare these two, your N1 is coming out to be 1, N2 is coming out to be 2. N1 here is 1, N2 here is 2. So in case of hydrogen, if electron makes a transition from 2 to 1, it will emit the same radiation. It will emit the same radiation which will be emitted here when the electron makes a transition from 4 to 2 in case of He positive. I hope this is clear. I hope this is clear to everyone. Now, my dear students, there is one more thing. There is one more thing from which question comes. How do you calculate the maximum spectral lines? How do you calculate the maximum spectral lines? There's a question. Maximum spectral lines obtained when electron makes a transition from higher to lower. There is a formula which I'm giving you. N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. This is the general formula by means of which you can calculate the maximum number of spectral lines. The maximum number of spectral lines which are obtained, right, when electron makes a transition from higher to lower. For example, what does it mean? Try to understand. Let's say this n is equal to 1. Let's say this n is equal to 2. Let's say this n is equal to 3. For example, electron is present in 3. It has to go from 3 to 1. Electron has to go from 3 to 1. Now, how many possibilities are there for the electron to go from 3 to 1? How many possibilities? Either the electron will go directly from 3 to 1, and if the electron is directly going from 3 to 1, it will emit one radiation. Or electron can go first to 2, then from 2 to 1. When it goes from 3 to 2, radiation. When it goes from 2 to 1, radiation. So in total, how many? In total, 3 radiations. In total, 3 spectral lines we get. 3 radiations which we get. Right? So a question is asked from here as well. Right? A question is asked from here as well. How many maximum spectral lines are obtained? And do remember, it is applicable for large number of atoms. It is applicable for large number of atoms. For example, I'm telling you that electron is making a transition from 6 to 1. How many maximum spectral lines it can emit? You will say the maximum number of spectral lines will be equal to, maximum spectral lines will be equal to N2 minus N1, N2 minus N1. multiplied by n2 minus n1 plus 1. So 6 minus 1 plus 1, 6 divided by 2. So the value will be 15. So in total, how many spectral lines are there? 15 spectral lines. Now, out of these 15 spectral lines, there will be some spectral lines which will fall in Lyman category. Some will fall in Balmer. Some will fall in Pasture. How do we check that? How do we check that? Do remember this as well. Number of spectral lines. Number of spectral lines. Number of spectral lines falling in a particular category. Falling in a particular category. Falling in a particular category is equal to higher energy state minus ground state of that series. What does that mean? What does that mean? What does that mean? For example, the question which I gave you, the electron was going from 6 to 1. In total, how many radiations it emitted? It emitted in total 15 radiations, 15 spectral lines. Out of these 15 spectral lines, there will be some spectral lines which will be falling in Lyman. Some will be falling in Balmer. Some will be falling in Pasture. How do we check that? See, if for example, I need to check in the same question, how many spectral lines fall under Lyman category is equal to higher energy state, that is 6 here, minus ground state of Lyman. Ground state of Lyman is 1. So out of 15, 5 spectral lines will fall in Lyman series. Then Balmer. Balmer. Higher energy state, that is 6, minus ground state of Balmer is 2. Right? Similarly, in Pasture, it will be 6 minus ground state of Pasture. Right? Bracket. 6 minus 4 is 2. Fund. 6 minus 5 is equal to 1. Correct? Check. 5 plus 4 plus 3 plus 2 plus 1. It will come out to be 15 only. So the total spectral lines which are obtained, right? Out of these total spectral lines, some will fall in Lyman category, some will fall in Balmer, some will fall in Pasture, etc. etc. Am I clear with this? Am I clear with this? Am I clear with this? Okay. So this is the result. These are the two results which I gave you. Can you try to solve this question? Can you try to solve this question quick? Quick, guys, quick, everyone. Hydrogen atom in ground state is excited by a monochromatic radiation of wavelength lambda. On coming back to ground state, 15 spectral lines are obtained. So hydrogen, the electron is in hydrogen, it's being excited. It goes to higher energy state. Then it again comes to ground state. Right? Let's say the higher energy state is N2. Let's say it came from N2 to 1. Perfect. When it is coming from N2 to 1, higher energy state to lower energy state, ground state 1, it is emitting how many? 15 spectral lines. So number of spectral lines is equal to N2 minus N1 multiplied by N2 minus N1 plus 1 divided by 2. Right? So 15 twos are 30 is equal to N2 minus N1 is 1. This will be N2, N1 is 1, 1 plus, this is simple, right? So what has to be the value of N2 so that this term becomes 30? So this has to be 6. 6 minus 1 is 5. 5 into 6 is 30. So N2 is 6. So basically you got to know your electron is making a transition from 6 to 1. You got to know that electron is making a transition from 6 to 1. And what, as per the question, you have to calculate? When the electron is making a transition from 6 to 1, the radiation which it emits, what is going to be its wavelength? So 1 by lambda is equal to R, Z square. It's for hydrogen, 1 upon N1 square minus 1 upon N2 square, right? So it's 1 divided by lambda is equal to R. It is 35 divided by 36. If I take the reciprocal, so lambda is 36 divided by 35 multiplied by 1 by R. 1 by R is 911.5 and the answer is going to be in angstroms. This is the lambda wavelength emitted, right? I believe this is clear to everyone. Look at this question. Electron in the hydrogen atom jumps from some higher energy level to third energy level. Let's say it is going from N2 to 3. If 6 spectral lines are possible for the transition, find the initial position. From 6 to, wait. Electron in the hydrogen atom jumps from higher energy level up to third. This is higher, right? This electron was present in higher energy state. Now it's coming to third energy state. Electron was present here. Now it's coming to third energy state. Perfect. This was the initial position of electron. This is the final position of electron. In total, 6 spectral lines are obtained. So number of spectral lines is equal to N2 minus N1, N2 minus N1 plus 1 divided by 2, right? So 6 2s is equal to 12 is equal to N2 minus N3. This will be N2 minus 2, correct? Now matter of calculation, solve it, get the value of N2. Right? Get the value of N2, and that N2 was the initial position of the electron. Perfect. Perfect, guys. So if N2 is 6, for example, if N2 is, for example, 6, 6 minus 3 is 3. 6 minus 2 is 4. 4 into 3 is 12. So that's fine. So N2 has to be 6. So electron was present at N is equal to 6. The electron is moving from 6 to 3. The electron is moving from 6 to 3. Look at this particular equation. In hydrogen-like atom, electron makes a transition from fourth excited state. Fourth excited state means N is equal to 5. Up to second state. Second state means N is equal to 2. Be careful. Excited state, fourth excited state to second state. So this is higher, this is lower. Then calculate the total spectral lines. Total spectral lines obtained is N2 minus N1, N2 minus N1 plus 1 divided by 2. So this is 4 multiplied by 5 divided by 2. So total 10 spectral lines are observed. Total 10 different spectral lines are observed, right? So this was your Broglie exactly suggested. As per this particular hypothesis is concerned, every matter present in the universe, having certain mass, moving with certain velocity. Every matter in the universe having certain mass, moving with certain velocity. It possesses wave nature as well. For example, I am the object, I have got certain mass, and I am moving with certain velocity. I have mass, I have velocity. That means I have momentum. Right? Momentum describes my particle nature. What de Broglie suggested, he said every object carrying certain mass, moving with certain velocity, has got wave nature as well. That means when I am moving with me, I have got a wave associated with me. And that wave, which is associated with an object moving with certain velocity, that wave you'll be calling as de Broglie's wave. And what he did, he gave a simple relation between the wavelength of that de Broglie's wave and the momentum of the particle, right? And he said lambda is inversely proportional to momentum. This is something which you have to remember. That means, for example, an electron is revolving around the nucleus. Electron has got mass, it has got velocity as well. So with the electron, there will be a wave associated with the electron. That wave which will be associated with the electron, that will be called as de Broglie's wave. And that de Broglie's wave will be having certain wavelength as well. And he said the de Broglie's wavelength of the wave which is associated with the particle moving with certain velocity is inversely proportional to its momentum. That is something which you need to remember, nothing else. So I'll say lambda is equal to h upon p. Or p you can write as mass multiplied by velocity. Okay? That means if this is the particle which has got certain mass, moving with certain velocity v, right? No doubt, if you calculate its linear momentum, p is equal to mv. It describes the particle nature. Of this particular object whose mass was m. Now de Broglie said When the object is moving, there will be a wave associated with it as well. And that wave he called as de Broglie's wave. And the wavelength of the de Broglie's wave is represented by lambda. And the result is lambda is equal to h upon p or h upon mv. Number one. This is the first result which you all must remember. Number one. Number two. You know, if I calculate the kinetic energy of this particular object whose mass is m, velocity is v, it's half of mv square. It's half of mv square. If I multiply and divide with mass, nothing will happen. Take this 2m here. So 2m multiplied by kinetic energy is equal to m square v square, which can be written as mv square. And m multiplied by v is p. So p square is equal to 2m multiplied by kinetic energy, or you can say momentum is equal to under root of 2m multiplied by kinetic energy, right? So my dear students, I can generalize one more result. De Broglie's wavelength is also equal to h upon, instead of mv, instead of p, you can write under root of 2m multiplied by kinetic energy of that particle, right, which we are talking about. Perfect. I believe these things are clear till here. I believe all these things are clear till here. Now there are few more results which I would want to share with you. Then we'll see different types of questions which can be asked. See guys, one more thing. If a charged particle is accelerated with voltage V. If a charged particle is accelerated, if you have got a charged particle, if you are accelerating the charged particle under the potential difference V, how do we calculate its de Broglie's wavelength? Its de Broglie's wavelength lambda will be calculated as under root of h upon under root of, this is 2m, this is q, charge on the particle, multiplied by the potential difference under which it is accelerated. Do remember this particular result as well. Okay. Now, for an electron, if an electron is accelerated at a potential difference of V, the de Broglie's wavelength associated with the electron is equal to 12.27 divided by under root of V angstroms. This result is particularly valid for an electron. Okay, this result is particularly valid for an electron. So how many results did we get till now? Lambda in terms of momentum, lambda in terms of kinetic energy, lambda in terms of the potential difference under which a charged particle undergoes acceleration, and this result is particularly valid for the electron. And at the same time, I can make one more result as well. You already know, as per your Bohr's theory, MVR is equal to NH upon 2 pi. If I write it like this, 2 pi R is equal to NH upon MV, does not make a difference. Take 2 pi here, MV here. Now H upon MV is something which you call as lambda. So 2 pi R is equal to N lambda. This is one more result which will be used in the questions. 2 pi R is equal to N lambda, right? From this particular result, a question can be asked. Similarly, there will be one more question asked. Number of waves made by an electron. While revolving around the nucleus. Is always equal to N. For example, if the electron is revolving in shell number 1, one wave will be made by the electron. If the electron is revolving in shell number 2, there'll be 2 waves made by the electron. If electron is revolving in shell number 3, there'll be 3 waves made by the electron. Right? Do remember all these results which are related particularly to your de Broglie's hypothesis. Right? And my dear students, if you think what kind of question is asked, look at the question carefully. A very simple and basic question. If kinetic energy of the proton is increased 9 times, you know your lambda is equal to h upon under root of 2m multiplied by kinetic energy. Right? Now, if kinetic energy is increased 9 times, what will happen to de Broglie's wavelength lambda dash? It'll be what? If this is 9 times, 9 comes out from the root as 3, right? So what will be the new de Broglie wavelength? Won't it be 1 divided by 3 lambda? Right? Won't it be 1 divided by 3 lambda? Or if you want to solve it as well, you can do that. Calling this is equation 1. Calling this equation now 1. Now, when kinetic energy is made 9 times, it becomes h upon under root of 2m multiplied by 9 times kinetic energy, right? Let's assume the de Broglie's wavelength now is lambda dash. If you do lambda dash divided by lambda dash divided by lambda, it will be 1 upon 3. So you can say lambda dash is equal to lambda divided by 3. So when kinetic energy is made 9 times, de Broglie's wavelength is reduced 3 times. It is made 1 by 3 times, right? So answer is 1 divided by 3. If you look at this particular equation, if you look at this particular equation, in hydrogen atom, if x is the radius of first Bohr's orbit, right? X is the radius of first Bohr's orbit. Then de Broglie's wavelength of the electron in third orbit. De Broglie's wavelength of an electron in third orbit. You know, 2 pi r. 2 pi r is equal to n lambda. This result you already know. We have to calculate de Broglie's wavelength in the third orbit. So it becomes 2 pi. Radius of third orbit becomes, if radius of first orbit is x, radius of third orbit becomes 3x. This becomes 3 times lambda. So 3 and 3 gets cancelled. Lambda is nothing but 6 pi x. This is the de Broglie's wavelength associated when the electron is in third orbit of hydrogen. Isn't it clear? Simple? Is it clear, people? Is it clear? Is it clear? Is it clear? Quick. Quick, guys. Just a second, sorry. There is a mistake which I did here. There is one small mistake which I did. I hope you realize that. If radius of first Bohr's orbit is x, radius of third Bohr's orbit will be, it is n square, right? It is n square. So it is 9x. Perfect. 3, 1, 3, 3. Now it's 6 pi x. Perfect. Now it is 6 pi x. I hope this is clear. It was supposed to be 3 square. Perfect. My dear students, now after this, if I give you one question, if I give you one small question, if an electron is accelerated, if the electron is accelerated at the potential difference of 9 volts, calculate the de Broglie's wavelength associated with the electron. Can you do it? If an electron is accelerated at 9 volts potential difference, calculate the de Broglie's wavelength associated with it. So it will be simply, for an electron, you know, lambda is equal to 12.27 divided by under root of V angstroms. So potential difference of an electron under which it's getting accelerated is given as 9. So it is 12.27 divided by 3, which makes it 4.09 angstroms. This is the de Broglie's wavelength associated with the electron, which is being accelerated under 9 volts. Right? Clear? This result already I gave you particularly for the electron. Right, people? I hope I'm clear till here. Now comes your Heisenberg's uncertainty principle. I'm not going into the details. I'll just tell you that amount of theory which is required to solve the equations. My dear students, as per your Heisenberg's uncertainty principle is concerned, the momentum and the position of a moving electron, or in general I can write of a microscopic particle. The momentum and the position of the electron, the momentum of the position of a microscopic particle cannot be determined simultaneously with 100% accuracy. Cannot be determined simultaneously with 100% accuracy. What does that mean? Let me make you understand it. Let me make you understand it. My dear students, for example, this is a nucleus. We say these are the shells as per your Bohr's theory, right? These are your shells in which electrons are revolving. These are your shells in which electrons are revolving, right? For example, I'm talking about this electron which is revolving here. Let's say I'm talking about this electron which is revolving here. My dear students, look carefully. If you want to locate this electron, if you want to see this electron in short, if you want to locate this electron, if you want to see this electron, what do you need to do? How do you see this electron? How do you see the object? How do you see the object? Simple, reflection of light. How do we see the objects? Simple, light falls on the object. It reflects back. It makes image in our eyes, right? So I want to see this object. I want to see this electron. I want to see this electron. So I'm thinking to use the same approach, the reflection of light. I'm thinking that I'll put some light on this electron. It will get reflected back, and this reflected ray I'll observe here. I can see the electron. This is something which I'm expecting will happen. I'll put the light on the electron, it will reflect back, and I'll see the reflected ray. But my dear students, we forgot one thing. What is light? We forgot one thing. What is light? Light is energy. When energy is incident on the electron, electron absorbs that energy. When electron absorbs that energy, it will start moving with higher speed now. It will start moving with higher speed. So, I wanted to see the electron. I wanted to locate the position of electron. But at the same time, electron absorbed that energy, started moving with higher speeds now. So when I wanted to locate the position of the electron, at the same time, there was uncertainty. There was error in the velocity. There was error in the velocity. And if there is error in velocity, that means there is error in momentum. Right? So my dear students, when I tried to locate the electron, there was uncertainty in the velocity. When I try to calculate the velocity, there'll be uncertainty in the position. So, in nutshell, position and momentum of a microscopic particle cannot be measured simultaneously with 100% accuracy. Position and momentum of a microscopic particle cannot be measured simultaneously with 100% accuracy. If you try to get the position of the microscopic particle, there will be error in its momentum. If you try to calculate the momentum, there will be error in its position. Right? And error in position, I'm representing with delta x. This represents error in position. Delta v represents error in velocity. Error in velocity. Delta p represents error in momentum. Error in momentum. Delta lambda represents error in de Broglie's wavelength. De Broglie's wavelength. Right? De Broglie's wavelength. Now guys, think carefully. You know, your P, momentum, is mass multiplied by velocity. Can I say error in momentum will be due to error in velocity? Because mass, I'm assuming constant. Error in momentum will be due to what? It will be due to error in velocity. So your delta P is basically equal to m delta V. M delta V. If you talk about lambda, lambda is equal to h upon mv. H is constant, m is constant, right? So whatever will be the error in wavelength, that error in wavelength is due to error in velocity. So error in de Broglie's wavelength can be written as h upon m delta V, right? Error in de Broglie's wavelength can be written as h upon m. This will be delta V. Perfect. Now, as per Heisenberg, error in the position dot error in momentum, it was observed to be greater or equal to h upon 4 pi. It was observed to be greater or equal to h upon 4 pi. You need not to know from where this result came, right? You need to remember this result, and I'll show you how to use this result in the questions. Number one. Number two. So I can write it like this: delta x dot delta p is nothing but m delta v, right? is greater or equal to h upon 4 pi. Or I can write it like this. Delta x dot delta v is greater or equal to h upon 4 pi m. This is one more way of remembering this equation. One more way of remembering this equation. Right? Perfect. Just a second. There is one more way of remembering this particular equation. You can remember it directly. Well, there's a proof as well, but I'm not showing the proofs and all. Delta x dot delta lambda is greater or equal to lambda square upon 4 pi. This is one more result which you can remember when it comes to Heisenberg's uncertainty principle. When it comes to Heisenberg's uncertainty principle. These are 3 results which you have to remember. Perfect. So in short, when you try to locate the position of the electron, there'll be error in its momentum. When you try to get the momentum of the electron, there'll be error in its position. So position and momentum of the electron cannot be measured simultaneously with 100% accuracy. If I try to locate the position, there'll be error in momentum. If I try to get the momentum, there'll be error in position. So both cannot be measured hand in hand with 100% accuracy. Right? Right, people? Perfect. And these 3 results you just have to remember. If you remember these results, there'll be questions based on these 3 results only. Nothing more than that. Am I clear? Am I clear till here? Let me know quickly in the chats. I want everyone to say it. If I'm clear till here, let me know quickly in the chats. Yes? Let me know quickly in the chats. Everyone. Everyone, people. Let's try to do few questions which will make it clear. Okay, before doing the question, there is one more thing which I want to share with you. My dear students, how do you get to know about the trajectory of the particle? How can you say that the particle is moving in this way, in this path, through this path? How can you say that? How can you say that? If you know the position and momentum of this particular particle, the position and momentum of this particular particle at every stage, if you know the position and the momentum of this particle at every stage simultaneously, that means if you know the position and momentum, if you know exactly the position and momentum of the particle, you can say the particle is here, then here, then here, then here, then here. So you can talk about the trajectory of the particle only if you know its position and the momentum at every point of time. But what Bohr said? Bohr said electron is revolving around the nucleus like this. That means Bohr said sometimes electron was here, then electron reached here, then electron reached here, then electron reached here. Bohr said it's a circular path. It is a circular path. Bohr said the trajectory is a circle here, almost a circle. Trajectory is almost a circle here. This is what Bohr said. But you can only talk about the trajectory. You can only talk about the trajectory if you know the position and momentum simultaneously with 100% accuracy. As per Heisenberg, can you get the position and the momentum of the electron simultaneously with 100% accuracy? No. That is the reason why Bohr's model was not accepted by Heisenberg. Is it clear? Is it clear? This gave rise to the quantum mechanical model. This was one of the major reasons which gave rise to the quantum mechanical model. Since Bohr said electron is revolving around the nucleus in the circular path, he said it's a circle which the electron is following, right? But you can only talk about the trajectory if you exactly know the position and the momentum simultaneously of the particle with 100% accuracy. But that cannot be done. So you cannot say electron was here, electron was here, electron was here. You cannot say electron was here. No. Therefore, from now onwards, we are going to talk in terms of probabilities. From now onwards, I'll say the probability of finding the electron at this position was something. Probability of finding the electron at this position was something. Probability of finding the electron at this position was something. Right? Perfect. So basically, Basically, according to Heisenberg, we can only define the probability of finding the electron around the nucleus. We cannot say with 100% certainty that electron is here, electron is here. No, you can say electron, the probability of electron to be here was this much. The probability of electron to be here is this much. We cannot say with 100% confidence, with 100% probability. No. Right? So from now onwards, we are only going to talk in terms of probabilities, probability of finding the electron around the nucleus. Okay? Probability of finding the electron around the nucleus. Right? Okay, look at this particular question. A particle with mass, you have got a particle which has got mass 10 raised power minus 10 grams. So it is 10 raised power minus 13 kilograms as per SI system. The velocity of the particle is nothing but 10 raised power minus 6 centimeter second inverse. Make it into meter. Make it into meter per second. You can do that, right? Right, people? So how much it will be in meter per second? It will be 10 raised power minus 8 meter second inverse. 0.001% uncertainty. So uncertainty in the velocity, that is delta V. Delta V is how much? 0.0001% of this value. Of this value. Right? Of this value. Of this value. This is the error in velocity. This is the error in velocity. This is the error in velocity. Perfect. Now what do we have to calculate? Delta x. You know, delta x dot delta v is greater or equal to h upon 4 pi. For the calculation purpose, you can say delta x dot delta v, you already got to know, 0.0001 divided by 100 multiplied by 10 raised power minus 8. For calculation purpose, you can use equality sign. H value, you know, 6.6 into 10 raised power minus 34, and 4 pi is nothing but 22 by 7. By solving this particular equation, you can get the value of delta x. Since I used every parameter as per SI system, so delta x will finally come out to be in meters. That is the error in position. That is the error in position. That is the error in position. Right? If you look at this question, an electron is accelerated from rest by applying a voltage of 6V. If electron is accelerated, how do you calculate its lambda? If electron is accelerated, how do we calculate its lambda? 12.27 divided by under root of V. V is 6, right? And it's going to be in angstroms. It's going to be in angstroms. Multiplied by 10 raised power minus 10 meters. So you got lambda. Delta x error in position is given to me as 7 upon 27 into 10 raised power minus 9 meters. What am I supposed to calculate? Delta lambda. I gave you few results. One of the result was delta x dot delta lambda is greater or equal to lambda square upon 4 pi. Now, my dear students, how do we calculate delta lambda? How do we calculate delta lambda? Delta lambda is nothing but h upon m delta v. H upon m delta v. Right? That's how you'll be calculating delta lambda. Wait, what are we supposed to calculate? We are supposed to calculate delta lambda. Okay. All right. There is no need to do this. There is no need to do this. We already are done. See, delta x, we are given with, this value we are given with, lambda value we already calculated, pi is constant, 4 is constant. From this particular equation, you can calculate delta lambda. You can calculate delta lambda, but I would suggest take every value as per SI system so that you get delta lambda as per SI system only. Right? This is one more type of the question which can be asked. Or there can be one more type of the question asked like this. If the error in velocity and position are same, if the error in velocity and error in position is same, what will be the error in de Broglie's wavelength? Error in de Broglie's wavelength is nothing but h upon m delta v, right? So basically h is constant, m is constant. We have to get the value of delta v. As per the question, error in position and velocity, they are same. Now you know, delta x dot delta v is greater or equal to h upon 4 pi m. If delta x and delta v are same, so it becomes delta v ka square is greater or equal to h upon 4 pi m. So I can say your delta v is greater or equal to under root of h upon 4 pi m. So you got delta v from here. If you got delta v from here, therefore delta lambda you can calculate h upon m. Delta v is under root of h upon 4 pi m. Perfect. So further you can do it like this, h upon under root of. This m goes into the root, m square, mm gets cancelled. This is hm divided by 4 pi. or you can take the root common. If you take the root common, this h becomes h square divided by. This becomes hm divided by 4 pi. That 4 pi goes up. 1h goes cancel, right? It will be under root of 4 pi h divided by m, right? This is the value of delta lambda, which is the error in de Broglie's wavelength, which we were supposed to calculate. Got it? Is it clear? My dear students, only these sort of questions will be asked when it comes to your Heisenberg's uncertainty principle, right? Now, if you talk about the quantum numbers, what are quantum numbers? Quantum numbers are basically the set of numbers which gives you the exact information about an electron in an atom. See, you know, in the atom there are shells, in the shells there are subshells, in the subshells there are orbitals. Now, if you want to know where the electron is, in which shell electron is, in which subshell electron is, in which orbital electron is, that is where quantum numbers are going to play a role. Quantum numbers, these are the set of numbers. These are the set of 4 numbers which give us the correct information about the electron in an atom. Which gives us the correct information about the electron in an atom. How many quantum numbers do we have? We have got 4 quantum numbers, right? These are the set of numbers which are required to locate the electron in an atom. One is called as principal quantum number, azimuthal quantum number, magnetic quantum number, and spin quantum number. We have got 4 quantum numbers. Out of 4 quantum numbers, these 3 quantum numbers, they are the outcome of Schrodinger's wave equation. The first 3 quantum numbers, they are the result of, they are the outcome of the Schrodinger's wave equation. This is not spin quantum number, it is not the outcome. It is not derived from Schrodinger's wave equation. There is only first 3 quantum numbers which are basically derived, which are the outcome of the Schrodinger's wave equation. Perfect. Now, let's talk about these quantum numbers one by one. My dear students, the first quantum number, that is your principal quantum number. That is your principal quantum number, which is represented by n. Okay. Principal quantum number, it gives us the idea about the size and energy of the shell. First of all, principal quantum number is going to let us know in which shell electron is present. In which shell electron is present. If n is equal to 1, n is equal to 1 represents the first shell, that is designated as K shell. If I say electron is in n is equal to 1, it means electron is in first shell, K shell, right? N is equal to L, n is equal to 3, M, n is equal to 4, N, right? So principal quantum number, it gives me the idea about the shell number. It lets me know that, it tells me that in which shell electron is present. Whether electron is present in first shell, second shell, third shell, fourth shell, etc., etc. Right? And this principal quantum number is the one which gives me the idea about the size and energy of the shell as well. Okay? You know, as the value of n increases, as the value of n increases, the size and energy of the shell automatically increases. Okay? Since you have studied radius of nth Bohr's orbit, r0 n square divided by z. N is involved here. Energy, total energy, minus 13.6 z square upon n square. N is also involved here. If you increase n, if n increases, radius of orbit increases. Radius of shell increases, right? The size of the shell increases. In the similar way, if n increases here, this is something which I told you already. When n increases, energy of the orbit increases. Perfect? So do remember from now onwards, principal quantum number, it gives me the idea about the shell number, number 1. Number 2, it gives me the idea about the size and the energy of the shell. As the n value increases, size as well as energy increases. The maximum number of electrons which can be accommodated in a shell, the maximum number of electrons which can be accommodated in the shell is equal to 2n square. That means in the first shell, how many electrons, maximum electrons you can accommodate? Put n is equal to 1, 2. Put n is equal to 2, 2 square, 4 2s are 8. Right? Put n is equal to 3, 3 ka square, 9, 9 2s are 18. Similarly, 4 4s are 16 to 32. Right? The maximum number of electrons which can be accommodated in a shell is always equal to 2n square. Right? This is all your principal quantum number tells us. Now, if you talk about the azimuthal quantum number, that is important. If you talk about the azimuthal quantum number gives us the idea about the subshell of a shell. Your shells are made of subshells, right? So principal quantum number gives us the idea about the shell. Now azimuthal quantum number, it gives me the idea about the subshell. It tells me in which subshell electron is present. In which subshell electron is present. In which subshell electron is present. So azimuthal quantum number, it represents a subshell within a shell, right? It gives you the idea about the shape of subshell as well. And every value of L represents a subshell. Every value of L represents a subshell. Understand now. How do we get the L value? L is from 0 to n minus 1. L is from 0 to n minus 1. Try to understand what exactly I'm going to say. If I talk about the first shell, right? What can be the possible values of L for the first shell? 0 to n minus 1, 0 to 1 minus 1. So L value is only 0. It is only 0. For n is equal to 2, L will be 0 to 2 minus 1. So 0 to 1. Right? Perfect. For L is equal to 2, it is between 0 to n minus 1, right? 0 to 2 minus 1, 0, 0 to 1, which tells you L is either, L can be 0, L can be 1. For n is equal to 3, L will be 0 to 3 minus 1, that means 0 to 2, which tells you it is 0, 1, and 2, right? I told you every value of L represents a subshell. How many values of L I got for the first shell? I got one value of L for the first shell, and that value was equal to 0. Here I got 2 values of L. Here I got 3 values of L. I told you every value of L represents a subshell. It tells you that in the first shell, there'll be one subshell. There'll be one subshell which will be designated as S subshell. In the second shell, there'll be 2 subshells, out of which one will be called as S subshell and one will be called as P subshell. Here, there'll be one S subshell, P subshell, D subshell, right? Similarly, if n is equal to 4, L will be 0 to 4 minus 1, 0 to 3. So 0, 1, 2, 3. Every value of L represents a subshell. So this is your S subshell, this is your P subshell, this is your D subshell, and this is your F subshell, right? So every value of L represents the subshell. Every value of L represents the subshell. So in your first shell, there is one subshell which is called as S. For S, the value of L is 0. Do remember it. If L value is 0, it represents S subshell. If L value is 1, it represents P subshell. If L value is 2, it represents D subshell. If L value is 3, it represents your F subshell. So every value of L here represents a subshell. So in the first shell, there is one subshell. In the second shell, there are 2 subshells. Third shell, 3 subshells. Fourth shell, 4 subshells. So can I say number of subshells in a particular shell? Can I say number of subshells in a particular shell for a particular shell is equal to the value of n? Is whatever is the n value, same number of subshells are there in a shell. Correct? Now, after this, you can calculate one more thing with the help of azimuthal quantum number, that is orbital angular momentum. For example, you have got 2s subshell. Let's say you have got 2p subshell. Let's say you have got 3s subshell, 3p subshell, 3d subshell. How do you calculate their orbital angular momentums? There is a formula, under root of L into L plus 1 into h upon 2 pi. If you talk about S, for S, L value is 0. If L value is 0, orbital angular momentum of 2s is 0. In case of P, L value is 1. So 1 plus 1, 2. So it is under root of 2 h upon 2 pi, which can be further written as h upon root 2 pi. If you solve it further, right? Because this 2 can be written as root 2 into root 2. 1 root 2, 1 root 2 cancel. For S, L value is 0. If L value is 0, orbital angular momentum 0. For P, L value is 1. If L value is 1, orbital angular momentum is this. For D, L value is 2. If L value is 2, 2 plus 1, 3. 3 2s are 6. So it becomes root of 6 h upon 2 pi. These sort of questions are also asked, right? You will be supposed to calculate the orbital angular momentums. And orbital angular momentum is nothing but under root of L into L plus 1 h upon 2 pi. Where L is 0 for S, L is 1 for P, L is 2 for D, L is 3 for F. Right? I hope this is clear. Now, my dear students, there is one more quantum number. That is magnetic quantum number, right? That is magnetic quantum number. Now, this magnetic quantum number, like we had principal quantum number giving the idea about the shell, azimuthal quantum number giving the idea about subshell. Magnetic quantum number gives me the idea about the orbital. In the shell, you have got subshells. In the subshells, you have got orbitals, right? So, magnetic quantum number, it gives me the idea about the orbitals in which the electrons will be present. And every value of magnetic quantum number m represents an orbital. Every value of m represents an orbital. Every value of m represents an orbital. And how do you get this m value? It lies between minus L to plus L. Minus L to plus L. Try to understand what it exactly means. Try to understand what it exactly means. For example, you have got S subshell. If I talk about S subshell, for S subshell, what is the value of L? L value is 0. If L value is 0, M will have its value from minus 0 to plus 0. Only 0. So how many values of M I got? One value of M, which is equal to 0. For P subshell, if you talk about P subshell, L will be minus 1 to L is 1 first of all. So M will be minus 1 to plus minus 1, 0 and plus 1. So 3 values of M. D subshell. L is equal to 2. If L is 2, M will be minus 2 to plus 2. So minus 2, minus 1, 0, plus 1, plus 2. Similarly, if I talk about the F subshell, L value is 3. If L value is 3, M can have values minus 3, minus 2, minus 1, 0, 0, plus 1, plus 2, plus 3. I told you every value of M represents an orbital. So how many values of M we have? 1. Here we have got 3 values. Here we have got 5 values. Here we have got 7 values. So in your S subshell, there is only 1 orbital. In your P subshell, there are 3 orbitals, which I represent with these squares. In your D subshell, there are 1, 2, 3, 4, 5. In your F subshell, there are 7 orbitals. 1, 2, 3, 4, 5, 6, and 7. 7 orbitals. This orbital I call as S orbital directly. This I'll be calling as, these 3 I'll be calling as P orbitals. One of them will be called as Px, one will be called as Py, one will be called as Pz. Similarly, these are your D orbitals. One will be called as dxy, one will be called as dyz, dzx, dx square minus y square, and dz square. These are the 5 d orbitals which are present in the D subshell. These are the 5 d orbitals which are present in the D subshell. For F, you have got nothing to do with the names of the F. Just remember, in the F subshell, there are 7 orbitals. There are 7 orbitals, right? Okay. Now, if you ask me, how do these orbitals look like? If you ask me, how do these orbitals look like? If I particularly talk about the shapes of orbitals, and then at the end, I'll talk about the spin quantum number. If you ask me, how these orbitals look like? So we have got S orbitals. If I talk about S orbital, let me tell you, S orbital, it is spherical. It is spherical in shape. It is spherical in shape. How it looks like? This is the nucleus, and these dots, they represent the electron density around the nucleus. They represent the electron density around the nucleus. So this is a spherical region where the probability of finding the electron is maximum. This is a spherical region. This is a spherical region where the probability of finding the electron is maximum. You must be thinking what an orbital is. Orbital, in simple words, I'll be defining it as a region around the nucleus. Orbital is basically the region around the nucleus where the probability of finding the electron is maximum, where psi square is maximum, where probability of finding the electron is maximum. So we have got a spherical region over here, wherein the probability of finding the electron is maximum. This spherical region over here, there's something which you will be calling as S orbital from now onwards. Okay? There's something which you call as S orbital from now onwards. If I talk about the P orbital, first of all, your P subshell has got how many P orbitals? It has got 3 P orbitals. One is called as Px, one is called as Py, one is called as Pz. One is called as Pz. How Px, Py, and Pz looks like? Just a second. If I talk about p subshell has got px, py, pz, right? These are 3 p orbitals. Now, first of all, if you talk about p orbitals are basically dumbbell in shape. They are basically dumbbell in shape. And how they look like exactly? Have a look. If I talk about px, if I talk about px, if I talk about px, imagine this is your y-axis and this is your z-axis. So this plane is your yz plane, right? This plane is your yz plane. And imagine this is your x-axis here. Okay? Imagine this is your x-axis, which is perpendicular to y and z. So there'll be one lobe of p over here, one lobe of p over here. This is how your p orbital looks like. And these lobes, they represent the electron density. Now, my dear students, do you see any plane? Do you see any plane cutting this orbital on which zero electron density lies, on which electron density is not present? There's a plane here, this YZ plane. This is the plane on which there is no electron density. Above the plane and below the plane, there is electron density. So this YZ plane is something here I'll be calling as the nodal plane. I'll be calling it as nodal plane, right? Similarly, if I talk about PY, how do you exactly make PY? How do you exactly make PY? PY, right? Call this as x-axis, call this as z-axis. So this is your y-axis. This is your y-axis, right? The electron density lies on this y-axis over here. Perfect. Do you see any plane over here wherein zero electron density lies? This xz plane. This xz plane here is the nodal plane. This is how your PY looks like. This is how your PY looks like. Similarly, if you talk about PZ, how your PZ looks like? Again, in the similar way. Again, in the similar way. Imagine this is your x-axis. Imagine this is your y-axis. And imagine this is your z-axis. And electron density lies along z-axis. These are the two lobes of your p orbital, right? There is a plane cutting the orbital in the middle in such a way that no electron density lies on that plane. And that plane is your nodal plane, which is here, the YZ plane, right? See, first I have to show Px, right? I had to show Px. So electron density has to be along x-axis. Then I had to show Py, electron density along y-axis. I was showing Pz, electron density along z-axis. That's why I interchange these axes. I hope this is clear to everyone. Similarly, if you talk about the shapes of your d orbitals, first of all, in case of your d subshell, how many d orbitals you have? In case of your d subshell, you have got 5 d orbitals. One is dxy, dyz, dzx, dx square minus y square, and dz square. Let me tell you, these two are what you call as axial orbitals. Axial d orbitals. Why axial d orbitals? Because their electron density, it lies along the axis. Electron density here lies along the axis. These three are what you call as non-axial d orbitals. Non-axial d orbitals, and electron density here lies between the axes. Between the axes. In coordination, you would have studied these are what you call as T2G, and these are what you call as EG set of orbitals. These are what you call as T2G set of orbitals. This is what you call as EG set of orbitals. Now, how these d orbitals exactly look like? That is the point. First of all, for example, I have to show dxy. Dxy. So first of all, let me show you the xy plane, this x-axis, this y-axis, right? If I talk about dxy, the electron density lies between these axes. All the d orbitals, first of all, your d orbitals are dumbbell in shape, double dumbbell, right? Your d orbitals, except dz square, all the others are double dumbbell shaped. They are double dumbbell shaped. As you can see over here, this is one of your dumbbell here, and this is one dumbbell. Perfect. This is your dxy. Do you see any plane cutting this orbital in such a way that no electron density lies on that plane? This is one of the plane which can cut this orbital in such a way that no electron density lies on it. This is one more plane, right? On which there will be no electron density. So how many nodal planes will be here? there'll be two nodal planes. And if I ask you, what are these two nodal planes? One will be xz plane and see this xy. So remaining planes is, one is xy, xz, and another one is yz. These are the two planes left. So these are the planes which represent nodal planes in dxy. Similarly in dyz, if you want to make the dyz, make this as the y-axis, make this as the z-axis. So this is one of the dumbbell, this is one more dumbbell. Perfect, right? This is double dumbbell. So how many nodal planes do you see here? This is one nodal plane, this is one more nodal plane. So there are again two nodal planes. If I ask you what is the name of those nodal planes, one is going to be xz, another one is going to be yx, right? Then you have got x, y, yz, zx. If you talk about zx, right, you can make it in the similar way. This is मान लो x-axis, this is your z-axis, this is your, this is your double dumbbell. This is one nodal plane, this is one more nodal plane. So again, there are two nodal planes. Again, there are two nodal planes, right? One will be yz, one will be xy. Yz and xy, right? Yz and xy. Perfect. These are your three non-action d orbitals. Then there are two more d orbitals. One is called as dx square minus y square, and one more is called as dz square. So dx square minus y square, it's simple. This is, imagine x-axis, this is y-axis. In your dx square minus y square, the electron density lies along the lobes. It lies along the lobes, right? Okay, this again double dumbbell. This is one of the dumbbells, and here this is one of the dumbbells, one more dumbbell. This is dx square minus y square. So how many nodal planes again? This is one nodal plane which cuts the orbital on which no electron density lies. This is one more nodal plane here, right? So again you have got two nodal planes. Again you have got two nodal planes. One is your yz nodal plane, one is your xz nodal plane. How this dz square looks like? How this dz square looks like? Dz square looks like this. This is x, this is your y. Okay. Just a second. Let me make it very clear. Let me make it very clear. Imagine this your x-axis. Imagine this your y-axis. So this is your xy plane. This is your xy plane, right? And this is how your dz square looks like. Apart from this, on this plane, you'll find electron density like this. It'll be a bangle like a structure. So electron density is present on xy plane as well. So xy plane is not the nodal plane here, right? See, this is the electron density, this is the electron density, and on the plane also the electron density is present. This is how your dz square looks like. This is how your dz square looks like, right? And dz square, it has got two conical nodal surfaces. This is one conical nodal surface. This is one more conical nodal surface. So do remember, dz square, it has got two conical nodal surfaces. It has got two conical nodal surfaces, right? It has got two conical nodal surfaces. Yeah, I hope I'm clear. Perfect. Now guys, let's talk about these nodes. Or before talking about the nodes, there was one more quantum number, which is what you call a spin quantum number, right? There was one more quantum number, which is what you call a spin quantum number. As you can see, spin quantum number, it represents the spin of an electron about its own axis. For example, this is the nucleus. Electron, it is revolving around the nucleus, for example. No doubt, it's revolving, but at the same time, it will be spinning as well. It is electron. Let's say this is your nucleus. Electron is revolving around the nucleus like this. Electron is revolving around the nucleus. But when electron is revolving, it is spinning about its own axis as well. It is spinning about its own axis as well, right? Perfect. If that spin is clockwise, that spin can be clockwise or can be anti-clockwise. That spin can be clockwise or can be anti-clockwise, right? Clockwise spin, the spin, right? It is either going to be clockwise or anti-clockwise. Clockwise we represent with 1/2 or upward sign. Anti-clockwise we represent with -1/2 or downward sign like this. So electron, during its, when it's the electron, it'll be spinning basically, right? It'll be spinning basically. It'll be spinning about its own axis. So for clockwise spin, spin is going to be taken as +1/2, and for anti-clockwise, it's going to be taken as -1/2, right? Right, people? Okay. Perfect. And the way we talked about the orbital angular momentum, under root of L into L plus 1 h upon 2 pi. Similarly, we have got spin angular momentum as well, under root of S into S plus 1 h upon 2 pi. I'll show you its application part in some time. But before that, there is something which is very important. What is that? That is the nodes. From nodes, you get the questions. What is a node basically, first of all? If you ask me, what is a node? I'll say node is a region. It is the region around the nucleus. Node is the region around the nucleus, wherein probability of finding the electron, is 0, is minimum. Or you can say psi square value is 0. Psi square represents electron density, right? It is 0. Okay? It is 0. Now, how do you calculate the total number of nodes? Total number of nodes are calculated by the formula n minus 1. This is the formula which gives you the total number of nodes. These nodes, exactly we classify them into two types. One is what you call as spherical nodes, or you can call them as radial nodes. One is called as angular nodes. How do you calculate spherical nodes? By the formula n minus L minus 1. Angular nodes are calculated with the help of L. L is the azimuthal contour number, right? Perfect. Now I'll show you the exact picture of these, how these orbitals exactly look like, right? For example, if I talk about 1s, in case of 1s, what is the value of n? N value is 1. What is the value of L for this s orbital? What is the value of L for s? 0. If I ask you how many total number of nodes are there, n minus 1. 1 minus 1 is 0, right? If I ask you how many angular nodes are there, angular nodes are represented by L. L value is 0, right? If I ask you spherical nodes, n minus L minus 1, n minus L minus 1, n minus L minus 1, that is 0. So there is no node. There is no node in 1s. So how this 1s looks like exactly? This is your nucleus, and this is the electron density here, which I'm showing. This is the electron density which I'm showing. Okay? And since there is no node means there is no region around the nucleus wherein electron density is 0. There is no region around the nucleus wherein electron density is 0. Okay? If you want to make a graph between psi square versus r or psi versus r, how these graphs will look like? See, psi can take both values, positive as well as negative, but psi square is always positive. So psi square graph, whenever you make, you will make always in first quadrant. It has to be always positive. But psi versus r, it can go downwards as well. Do remember, all your graphs, all the graphs of s orbitals start from top. Just said this is the technique by means of which you can remember. The approach is otherwise different. I have to show you the Schrodinger's wave equation. That is very hectic. No, that's of no use to you. Just remember it like this so that you can solve your questions quickly. All your graphs of s orbital, they start from top. Okay. Now, first of all, In case of s orbitals, closer to the nucleus, electron density increases. Closer, as you go closer to the nucleus, electron density increases. The probability of finding the electron is more. As you go closer to the nucleus, probability of finding the electron is more in case of s orbital, right? So as you go closer, psi square value is increasing. Psi square value is increasing. As you go far, psi square value is decreasing, right? So the graph will be like this. This graph won't be touching the r-axis, because if this graph touches the r-axis, at that point, psi square will be 0. Psi square 0 means node. Electron density 0. That means node, but there is no node, right? Just repeat the same graph here. This is for 1s. Anything can be asked for 1s from this particular slide. Then if I talk about the 2s, what is the value of n? N value is 2. L value for s is 0. If I ask you total number of nodes, n minus 1. So 2 minus 1 is 1. If I ask you about the angular nodes, angular node is value of L. L value is 0. If I ask you about spherical node, n minus L minus 1. Spherical node is 1. So how many total nodes are there? 1. And which node this is? This is spherical node. This is spherical node. Spherical node, that means in 2s you will see one spherical region. In 2s you will see one spherical region wherein the probability of finding the electron will be 0. Right? For example, see how you are going to remember this. This is the nucleus. And this is your 1s. This is your 1s. After your 1s, there will be a spherical region wherein electron density will be 0. Right? And after that region, electron density will again start. After that region, electron density will again start. This is how you are going to remember it. Okay, this is your 1s. After that, you can see this open space here. One spherical region you can see here. This is the spherical region in which electron density is 0. This is the spherical region wherein electron density is 0. So it represents your spherical node, or you can call it as radial node. You can call it as the radial node. Okay, you can call it as the radial node. Perfect. Now, if you want to make the psi square versus r graph here, you can do that. So if you want to make psi square versus r curve, or you can make psi versus r curves as well. As I told you, psi value can be positive as well as negative. So the graph can be in first quadrant as well as below, right? But psi square will be always above in the first quadrant itself. Now, understand. See, closer to the nucleus, electron density is maximum. As you go far from the nucleus, electron density decreases. As you go far from the nucleus, electron density decreases, right? Then there's a node. This is a node here. There's a region where the electron density is 0. This is the node. After the node, electron density again goes up. Electron density again comes here. Then it further decreases, right? So this point over here represents a node. Okay? If you want to make psi versus r, as I told you, psi can have positive as well as negative values, right? In reality, first we make psi versus r curves only. Right? First we make psi versus r curves only. Then that part of the curve which goes down the r-axis, we take its reflection. That's why it becomes then like this. That's why it's like this for psi square versus r. Okay? First, actually, we make psi versus r curve. Then if we have to make psi square versus r, so that part of the curve which goes down the r-axis, its reflection is to be taken. That's it. It automatically becomes your psi square versus r. Right? Sir, these won't come in NEET. Look at your syllabus. They have clearly mentioned psi and psi square curves for 2s and 2p. Right? Okay? Hariharan, please do not become a leader here. Just focus on what I'm teaching, okay? You're just coming and telling things in the chats and leaving, right? I did not see you throughout the session. Now you are coming to the session and saying this, that. Your 65 to 70% portion is complete in game of NEET. The remaining portion is done here. So technically we have to do 35% only. So if you have been following game of NEET, follow this 35%, your syllabus is complete. Okay? I hope this is clear to everyone. right? This was your 2s. Okay, if I ask you how your 3s looks like, how your 3s exactly looks like, can you let me know how 3s will look like? How 3s will look like? First of all, it is the s orbital again. So n value is 3, l value is 0, total number of nodes n minus 1, right? Spherical nodes, n minus l minus 1, angular nodes is equal to l is 0, so angular node 0, right? So how you will make your 3s? How you will make your 3s? This is the nucleus. This is what you call your 1s. How many spherical nodes are there? There are 2 spherical nodes, right? So there will be 2 spherical regions wherein the probability of finding the electron will be 0, right? So I showed 1s. After 1s, there will be 1 spherical region, blank region. Then your 2s will start. This is your 2s. This is your 2s. So how many spherical region I showed till now? 1. Now there will be 1 more spherical region because I have to show 2 spherical regions. So after 2s, there will be 1 more spherical region. Then your 3s will start. Then your 3s will start like this. Right? So how many spherical regions you have? 1 and 2. So there are 2 spherical nodes. There are 2 spherical nodes. Now how do you remember it? How do you remember the psi square? Psi square versus r graph and psi versus r. And psi versus r. How do you remember it? How many nodes do I have to show? I have to show 2 nodes. I need to show 2 nodes. I need to show 2 nodes. Tell me one thing. Since I need to show 2 nodes, correct? All the S graphs, they start from origin. I have to show 2 nodes. So this is your 1 node, right? This is your 2nd node. And that's it. These are your 2 nodes here. At this point, psi square is 0. At this point, psi is 0, right? Perfect. Now guys, if you want to make psi square out of it, take the reflection of that part which is below. That means this part, its reflection has to be taken. So the graph looks like this. Right? These are the 2 nodes here. These are the 2 nodes in case of 3s. I believe this is clear. Okay? I believe this is clear. Right? All right. Let's move on to P. Let's move on to P. If I talk about 2P. 2P. Remember, in case of 2P, your psi and psi square, those they start from origin. They start from origin. They do not start from top, they start from origin. How exactly? How exactly? Have a look. If I talk about 2P, n value is 2, L value for P is 1, L value for P is 1, total number of nodes. Total nodes is n minus 1, 2 minus 1 is 1. Spherical nodes, n minus L minus 1. So n minus L minus 1. Spherical nodes will be 0, right? Okay, angular nodes. Angular nodes, L value is 1, angular node is 1. So there are in total 1 node, and that 1 node is basically your angular node. That 1 node is basically your angular node, correct? Now, how this P looks like? P is dumbbell shaped, right? So this is your nucleus. This is your 1 lobe, this 1 more lobe, right? Okay, this is your 2P. Now, my dear students, you have got the angular node here. What is an angular node? Angular node. Angular node is a plane. Like I showed you nodal plane, right? Angular node is a plane which cuts the orbital in such a way that no electron density lies on that, right? If you cut the orbital in between, like this is the plane wherein electron density will be 0. And you call this plane as the angular node. You call this particular plane as the angular node. Okay. Now, if you will have to make the graph between psi square versus r and psi versus r, you can do that. You can do that. I told you these graphs start from origin. These graphs start from the origin, from here. So already you are representing a node. Perfect. Now this goes up, comes down. This goes up, comes down. Correct? Already they are representing a node here. Perfect. This is your 2P. This is your 2P. Okay. Since I made the psi versus r first, then I was supposed to see is any portion going down r axis. Then I was supposed to take its reflection. There was no portion going down. Right? This is how your 2P looks like. Okay. Talking about your 3P. talking about your 3p. N value is 3. L value is how much? L value is 1. Total number of nodes. N minus 1. 3 minus 1 is 2. Out of which angular nodes are how many? L value is equal to 1. So angular node 1. Spherical node N minus L minus 1. N minus L minus 1. Spherical node is 1. So in total there are 2 nodes, out of which one is angular, one is spherical. Out of which one is angular, one is spherical, right? So imagine this is the nucleus. This is your 2p, right? This is your 2p. So already one node is included here, right? One node is included here. Which node is that? This is your angular node here. This is your angular node here, on which electron density is 0. Now, this is 2p, correct? But I have to make 3p. I have represented one angular node. I have to show one spherical node as well. I have to show one spherical node as well. So I have to show one spherical region on which electron density will be 0. So there will be one spherical region like this. Right? Do you see in between a spherical region? Here you have got a spherical region. Here you have got a spherical region wherein electron density is 0. So this node, this is your basically spherical node and this your angular node. So if you want to make a graph between psi versus r, or let's say psi square versus r, and then you have got psi versus r graph, you can make it. You can make it. In case of p, all the graphs, they start from origin, right? So I'll start from origin. How many nodes I have to represent? 2. One is already represented. This is second. That's it, right? Psi square. Take the reflection of this part. Okay, so it will be like this. Then, correct? Correct, people? These are your 2 nodes here, out of which this one represents the radial node. Okay? I hope this is clear. I hope this is clear. So I believe you can make for 3p, 4p, 5p, etc., etc. You can do that on your own. Correct? So all these questions can be asked in your examination as well. For example, I'm giving you a question. Psi square versus r. Okay? Can you tell me for which orbital it belongs to? Can you tell me for which orbital it belongs to? First of all, the graph is starting downwards. It's p. It is p. Now, how many total nodes do you see? 1, 2, 3, 4. Total nodes. So n minus 1. Total number of nodes is 1, 2, 3, 4. N value is 5. It is your 5p basically. Do you get it? It is your 5p basically. For example, I'm making a graph like this. I want you guys to answer this. Let's say this is psi. Let's say this psi versus r. I'm starting from here. Okay. First of all, the graph is starting from the top, so it's S. 1, 2, 3, 4. 4 nodes. So total number of nodes is 4. So n minus 1 is 4. That means n is 5. So it is 5s. Got it? I hope all these questions can be solved easily. Correct? My dear students, if I have to convert this 3p into 4p, in 4p there will be 3 nodes. 1 angular and 3 radial. 3 spherical. 3 spherical. This is your 1 angular. Sorry, 1 in your 4p, in your 4p, there will be total 3 nodes. 1 will be angular and 2 will be spherical. So this is angular, this is spherical. Now after this, I have to show one more. After this, I have to show one more region. Correct? After which electron density starts. Now it represents what? Now it represents 4p. Now it does not represent 3p now, it represents 4p now. I hope you can make all these now. Right? I hope you can make all these now. I hope everything is super clear till here. Right? Okay? Guys, one topic which I am leaving as such, which I would want you guys to do on your own, that is your electronic configuration. Right? In your electronic configuration, you must be knowing only one question comes. That's your chromium electronic configuration and copper. Right? This is 3D 5 4s1 and this is 3D 10 4s1. Over here, half filled configuration is more stable, and over here, fully filled configuration is becoming more stable. Why half filled is more stable? There are 2 reasons. one is symmetry, leads to stability, one is your exchange energy. Right? I mean electronic configuration part, that I believe you would have already done, right? Electronic configuration part you can do on your own. Okay. Anyways, in the PDF, I'll put this electronic configuration part as well in the PDF. Is this chapter like proper clear to you now? Is this chapter like proper clear to you? Honestly, I would want your answers. Is this chapter properly clear to you? I would want the genuine answer, please. Yes? Is it like done and dusted? That's wonderful. So one topic, please, and please do not skip that. That's electronic configuration. You are going to do that on your own. Okay? That's great. That's great. Will you be able to do electronic configurations on your own? That is one part, one small part of the chapter, electronic configuration. Are you sure you'll be able to do it on your own? Yeah? Add your super, sir. I fail to understand what are you saying. I'll share the PDF today. I'll share the PDF for sure. For sure, I'll share it. Anything else? Next chapter is going to be this amines. Amines I'll be doing. That's going to be our next chapter. Okay. And by the way, I'll be taking one more session on this atomic structure. Okay, let's do one thing. The session which I'm going to take, top 100 questions, right, of atomic structure. Let's do that day after tomorrow, in which I'll solve some 100 questions of this atomic structure chapter with you, so that whatever doubts will be there in between, they get clearer too, right? Okay. Right? I hope all the things are absolutely clear to you and atomic structure chapter is clear to you. Now please go through the NCRT once. Read the theory part of the NCRT from this particular chapter. And day after tomorrow, I'll be doing top 100 questions of atomic structure. And I believe with that, it will be done and dusted. Yes? Perfect. Do let me know in the comment section of this video. How did you like it? Hello, see you in the next session. Take care. God bless you all. Bye-bye. Take care, guys. Take care.